Right now, in the cold, silent depths beyond the edge of our solar system, two human-made objects are drifting farther from Earth than anything else we've ever built. They are small, fragile, and powered by the last fading traces of radioactive decay. But they carry with them the story of our entire planet. Voyager 1 and Voyager 2 were launched not just to explore other worlds, but to push the limits of what was possible and to leave a piece of humanity behind in the vastness of space. What started as a daring plan to visit the outer planets quickly turned into one of the greatest journeys in the history of science. Along the way, they revealed hidden volcanoes, strange magnetic fields, icy oceans, and new mysteries at the edge of the solar system. Their journey is still not over, and neither is our fascination with them. The Grand Tour: Origins of the Voyager mission. In the early 1960s, excitement was building among the scientific community. The planets were aligning into a rare formation. It would be a once-in-a-lifetime chance to visit many of them in a single trip, using a clever trick of gravity to slingshot from one world to another. This rare planetary alignment, set to happen in the late 1970s, sparked a vision known as the Grand Tour. But it would take far more than dreams to turn this idea into reality. It would need diplomacy, negotiation, and the slow, steady building of political and scientific support during a time when every dollar spent in space had to be justified. Scientists at NASA's Jet Propulsion Laboratory, or JPL, along with researchers from universities across the country, began to recognize that the outer planets, Jupiter, Saturn, Uranus, and Neptune, would soon line up in a way that happens only once every 176 years. A spacecraft launched during this window could visit all four, traveling faster and farther than ever before. Gravity assists from each planet would help propel the spacecraft onward, like a stone skipping across a river. The excitement in scientific circles was undeniable, but the challenge was immense. At the time, planetary exploration was still in its infancy. America's first successes with spacecraft like Mariner 2 and Mariner 4 were very recent, and every mission faced enormous risks. Asking Congress to approve a mission that would stretch over more than a decade, cost hundreds of millions of dollars, and risk complete failure was not an easy task. In Washington, support for space exploration waxed and waned. The Apollo program had captured the world's attention, but as costs soared, the political appetite for new, expensive space missions began to shrink. NASA scientists knew they had to tread carefully. They began informal talks with key figures in Congress, quietly spreading the word about the opportunity. The National Academy of Sciences got involved too, recognizing the immense scientific value of such a mission. They issued reports stressing the importance of exploring the outer planets, highlighting the mysteries of their atmospheres, moons, and magnetic fields. These reports, written in clear, persuasive language, were meant to arm NASA officials with the tools they needed to argue their case. The idea faced strong headwinds. In the late 1960s, America was caught in the turmoil of the Vietnam War. Budgets were tight. Skepticism toward large government projects was growing. Some policymakers asked why America should spend money exploring distant planets when there were problems at home that needed urgent attention. NASA administrators understood they needed to find a way to scale the mission so that it looked less like a gamble and more like a logical, manageable next step. Behind the scenes, a delicate balancing act unfolded. Scientists pushed for an ambitious multi-planet mission. Budget officers pushed back, wary of costs and risks. Meanwhile, engineers quietly studied ways to design spacecraft that could survive the long journey, even though formal approval hadn't yet been granted. One of the key strategies that emerged was the idea of building off-ramps into the mission plan. The spacecraft would be designed to visit at least Jupiter and Saturn, a major achievement in itself, with the possibility of continuing to Uranus and Neptune if they survived, and if funding allowed. This approach gave NASA a strong fallback position. If political winds shifted or technical problems arose, the mission could still achieve valuable science without needing to justify the full Grand Tour up front. At the same time, advocates for the Grand Tour worked to build broader public and international support. They knew that political leaders were more likely to back the mission if it was seen as a symbol of American ingenuity and leadership. Scientists gave talks at universities, wrote articles for popular science magazines, and participated in television specials about space exploration. These efforts helped keep the idea alive in the public imagination, even as the formal political battles continued. The diplomatic side was equally important. NASA reached out to scientists in Europe and elsewhere, discussing the possibilities for international cooperation. While no firm partnerships would emerge at that stage, these conversations helped position the Grand Tour as a mission for all humanity, not just for one nation. In 1969, as astronauts walked on the Moon for the first time, the Grand Tour was still just an idea on paper. But momentum was building. Key officials within NASA, such as Homer Newell and James Fletcher, became strong supporters. They worked carefully with the Office of Management and Budget and with Congress to shape a funding request that seemed reasonable, even cautious, while still keeping the dream alive. The original vision, involving 4 or even 5 spacecraft visiting every outer planet, was slowly pared down. Instead, the plan evolved into a proposal for 2 spacecraft, designed with enough durability and flexibility to possibly complete the whole tour if everything went well. It was a compromise, ambitious enough to capture the imagination, realistic enough to survive political scrutiny. By the early 1970s, after years of quiet lobbying, strategic compromises, and careful planning, NASA finally received approval to move forward. The mission would be called Voyager. It would not formally promise to carry out the full Grand Tour. That language was avoided in official documents to keep expectations grounded, but the opportunity was still there, waiting. Engineering for eternity, designing probes to outlast decades. When it came time to design the Voyager spacecraft, the engineers knew they were facing a monumental task. The spacecraft would need to survive, not just for years, but for decades. No one could send a repair team, no one could refuel it or replace a broken part. Once Voyager left Earth, it would be completely on its own. If something went wrong millions or even billions of miles away, there would be no second chance. The first challenge was the environment itself. Space is not a gentle place. It's a vast, cold, radiation-filled vacuum. Near Jupiter, Voyager would face radiation levels thousands of times greater than Earth's natural background levels. In the outer solar system, the spacecraft would be plunged into deep cold, far colder than any natural place on Earth. The hardware would have to survive being baked by the sun early in the mission, and then frozen in the blackness near Neptune. Choosing the right materials became a critical job. Engineers at JPL spent years studying how different metals, plastics, and coatings would hold up over time. Aluminum was selected for much of the spacecraft's structure because it was lightweight yet strong, and it didn't become brittle in extreme cold. Titanium was used in parts that needed extra strength without added weight. Every wire, every connector had to be tested to be sure it wouldn't crack or corrode after years in deep space. Electronics in particular are vulnerable to radiation damage. A strong burst of radiation can flip bits inside a computer or even burn out entire circuits. To protect Voyager's delicate brain, engineers chose specially hardened components. They also physically shielded key parts of the spacecraft with additional layers of insulation, and even by careful placement inside the spacecraft body, using the bulk of the probe itself as a shield. Redundancy was a crucial strategy. Where possible, Voyager was designed to have backups. It carried 3 computers, not 1. It had duplicate transmitters, duplicate receivers, and duplicate attitude control systems. If one system failed, another could take over. In some cases, even a third level of backup existed, but redundancy added weight. And weight was always a concern, so engineers had to make careful decisions about what to double and what to leave as single points of failure. Voyager would travel far beyond the reach of solar panels, where sunlight was too weak to provide power. Instead, it carried radioisotope thermoelectric generators, or RTGs. These were simple, reliable power plants that used the heat from decaying plutonium to generate electricity. RTGs had no moving parts and could produce power steadily for decades. But even the RTGs would slowly weaken over time as the plutonium decayed and the generators aged. Engineers had to plan for a gradual decline in available power, designing systems that could be turned off one by one as needed to keep the most important functions alive. Every component, every system was subjected to brutal conditions that mimicked what it would face in space. Hardware was baked in ovens to simulate the heat of launch and early spaceflight. Then it was frozen in vacuum chambers to simulate the cold of deep space. Electronics were blasted with radiation to see how much they could survive. Mechanical parts were run through thousands of cycles of use to reveal hidden weaknesses. Some systems were even vibrated violently on giant shakers to simulate the stresses of launch. If something failed, engineers studied why, redesigned it, and tested it again. Software reliability was just as important as hardware. Voyager's computer systems had very little memory by today's standards, less than many modern wristwatches, but they had to be absolutely reliable. Software had to be simple, rugged, and able to recover from unexpected problems. Engineers wrote code that could detect when something was wrong and try to fix it automatically. If that wasn't possible, the spacecraft would wait for instructions from Earth, even if it meant waiting days for a command to travel across the vast distances. Instead of making the probe clever and autonomous, engineers made it tough and steady. Voyager would not try to outthink problems. Instead, it was built to be slow, cautious, and persistent. If a maneuver was needed, Voyager would execute it carefully, check itself, and report back to Earth before proceeding further. This deliberate style of operation reduced the chance of small mistakes, compounding into mission-ending disasters. Voyager's antenna, a 12-foot wide dish, was another example of smart engineering for the long haul. The antenna would have to stay pointed at Earth across unimaginable distances, with no room for error. It was built with rigid materials that would not warp over time, even after exposure to radiation and temperature swings. The spacecraft's attitude control system, which used small thrusters to adjust its orientation, was designed with high precision, but also with fuel efficiency in mind, since the supply of thruster propellant would have to last for decades. Voyager's instruments were selected not only for their scientific value, but also for their expected durability. Instruments with moving parts were minimized whenever possible. Mechanical systems tend to fail first, so if a scientific instrument could be made solid state, with no moving parts, that was preferred. Where movement was necessary, such as in the scan platform that moved cameras and detectors, engineers designed for strength and redundancy, and they included safety modes that could lock the platform into a fixed position if problems developed. Critical systems were placed in the warmest, most protected parts of the spacecraft body. Less critical systems were placed toward the outer edges. Cabling was routed in ways that minimized exposure to stress or radiation. Thermal blankets were wrapped around the spacecraft to help regulate temperature, keeping sensitive electronics from freezing or overheating. Perhaps most remarkable of all was the mindset the engineers adopted. They understood that they were building something that might outlive them. Voyager wasn't just a mission. It was a legacy, a message in a bottle flung into the cosmic ocean. That awareness shaped every decision, large and small. It demanded humility, patience, and a refusal to take shortcuts. There were countless moments of doubt. Would the computers fail after a few years? Would the RTGs produce enough power after 2 decades? Would the spacecraft's thrusters clog or seize up from disuse? No one could know for sure. But by planning for failure at every step, by assuming things would go wrong and designing ways to work around them, the engineers gave Voyager a fighting chance. The final spacecraft that emerged was not flashy. It was a simple, elegant machine, sturdy rather than sophisticated, built to endure rather than impress. Voyager was not meant to be perfect. It was meant to last. And through the long, silent decades that followed, as it crossed the boundary of the solar system and moved into interstellar space, it would prove just how well its builders had done their job. Thermal beacons, the role of RTGs in sustaining Voyager. In the early days of the Voyager project, the question of how to power the spacecraft was one of the biggest challenges. Solar panels had worked well for earlier missions close to Earth, like the Mariner probes that explored Venus and Mars. But beyond Mars, sunlight grows weak. By the time a spacecraft reaches Jupiter, sunlight is about 25 times dimmer than it is near Earth. At Saturn, it's 100 times dimmer. At Uranus and Neptune, it's even worse. Using solar panels would have meant building massive heavy arrays, far larger than any ever flown before, just to generate the small amount of power Voyager would need. These panels would have made the spacecraft heavy and difficult to launch, and even then, they might not have produced enough energy to run its instruments and communications equipment. Batteries eventually run down. No chemical battery could last for the decades Voyager would need. Some battery systems might have lasted a few years, but not the 10, 20, or even 30 years the Voyager team was aiming for. Batteries would have meant a ticking clock from the moment Voyager left Earth, and that was simply not acceptable for a mission designed to explore the very edge of the solar system and beyond. RTGs didn't rely on the sun or on stored chemical energy. Instead, they used the natural decay of a radioactive material to produce heat. This heat was then converted directly into electricity using solid-state thermocouples, devices with no moving parts. As long as the plutonium continued to decay, the RTGs would continue to produce power, slowly and steadily, year after year. The choice of plutonium-238 was critical. Unlike plutonium-239, which is used in nuclear weapons, plutonium-238 is almost useless for bombs. Its main property is that it gives off a lot of heat through natural radioactive decay. It doesn't explode, it simply warms up. A small block of plutonium-238 glows red-hot, even in the darkness of space. Each Voyager spacecraft carried 3 RTGs, mounted on a boom that extended away from the main body of the spacecraft. This kept the radiation from the RTGs away from the sensitive scientific instruments. It also helped balance the spacecraft for better stability during flight. The RTGs themselves were built to be rugged. Each contained ceramic pellets of plutonium dioxide, packed into sturdy shells designed to survive the rigors of launch, possible accidents, and the harsh environment of space. The RTGs performed 2 vital tasks for Voyager. First, they provided electrical power, about 470 watts at the start of the mission. That might not sound like much. It's less than the power used by a typical household microwave. But it was enough to run all of Voyager's systems, from its communications to its cameras to its science experiments. Second, the RTGs provided heat. Spacecraft electronics don't just need to be kept from overheating, they also need to be kept from freezing. In the deep cold of space, with temperatures approaching absolute zero, the gentle warmth from the RTGs helped keep Voyager's instruments and fuel lines from freezing solid. Because RTGs have no moving parts, there was almost nothing mechanical that could wear out or break down. The thermocouples that converted heat to electricity were simple, rugged devices made of metal and semiconductor materials. They degraded slowly over time, but not enough to threaten the mission. And the plutonium decay itself was utterly predictable. Plutonium-238 has a half-life of about 87.7 years, meaning it takes nearly 9 decades for half of it to decay. This slow, steady process gave Voyager a long, gradual decline in power, not a sudden loss. From the beginning, engineers knew that Voyager's available power would drop year by year. They planned for this. Even today, long after the spacecraft's prime mission ended, Voyager continues to operate, with careful management of its remaining power. Solar panels, if used in the outer solar system, would have been vulnerable to micrometeoroids and radiation damage. A single sharp particle or a burst of high-energy radiation could damage a panel badly enough to cut off power. But the thick-walled RTGs were built to shrug off such hazards. As long as the plutonium remained intact inside its protective housing, Voyager would continue to have power. The development of the RTGs for Voyager built upon earlier experience. NASA had used RTGs in previous missions, including the Apollo lunar surface experiments and the Pioneer probes that first explored Jupiter and Saturn. But Voyager pushed the technology further, demanding longer life, higher reliability, and greater safety. Every RTG underwent extensive testing to make sure it could survive accidents on Earth, such as a launch failure, and still operate properly once in space. Engineers tested the RTGs against impacts, fires, and re-entry into Earth's atmosphere, covering every scenario they could imagine. The idea of sending radioactive material into space naturally raised concerns. Public protests and legal challenges occurred before launch, with some people worried about the consequences of a launch accident spreading plutonium over wide areas. NASA and the Department of Energy took these concerns seriously. They conducted detailed safety studies, designed the RTGs with multiple layers of shielding, and worked closely with independent reviewers to make sure the risks were as low as possible. In the end, Voyager's RTGs were launched safely aboard Titan III rockets in 1977, without incident. Today, more than 4 decades after launch, the RTGs continue to power the spacecraft, though at reduced levels. Some instruments have been turned off, and more will follow as the available power drops. Eventually, even Voyager's ability to communicate with Earth will end, but the RTGs have already far outlived the expectations of their designers. The decision to use RTGs on Voyager stands as one of the clearest examples of how thoughtful engineering can extend the life of a spacecraft far beyond what anyone dared hope. It was a choice rooted in patience and long-term thinking. The quiet, steady heartbeat that has carried Voyager through the cold and empty spaces between the stars. Golden Record debates and design choices. While engineers and scientists were building Voyager to survive the harshness of space, another group was working on something far different, a message. It would be small, no larger than a record album. A time capsule meant for any intelligent life that might someday find the Voyager spacecraft floating among the stars. A few years earlier, plaques had been placed aboard the Pioneer spacecraft. These simple metal plates had line drawings of a man and woman, a sketch of the spacecraft's origin near the Sun, and a few other pieces of basic information. But with Voyager, there was a feeling that more could be done. The spacecraft was expected to travel farther and last longer than anything before it. If this was to be humanity's ambassador to the galaxy, it deserved a message that was richer, more layered, and more meaningful. The man chosen to lead the project was Carl Sagan, an astronomer known for his passion for public science. Working with a small team that included Frank Drake, Ann Druyan, Timothy Ferris, Linda Saltzman-Sagan, and John Lomberg, Sagan set out to create a message that was at once scientific, artistic, and deeply philosophical. One of the first debates centered around what kind of message humanity should send. Was it better to present a technical, scientific view of Earth, measurements, maps, equations, or should the message focus on the emotional and cultural richness of human life? Should the record be serious and formal, or playful and warm? Some believed it should show our best side, an idealized version of humanity, while others thought it was more honest to include the full range of human experience, even the painful parts. In the end, the team agreed that the record should show a mixture, a greeting from a scientific civilization that was also capable of art, music, love, and dreams. They wanted to show that humanity was not just a species that could build rockets, but also a species that sang, danced, and wondered about its place in the universe. The golden record would carry sounds and images, but only a few hundred total. Every choice had to count. For the images, the team selected photographs and diagrams showing the diversity of life and culture on Earth. There were pictures of landscapes, mountains, rivers, deserts. There were pictures of animals, birds, insects, fish, and mammals. There were pictures of human beings, men, women, and children, from many cultures and places. The team spent hours debating the details of these images. Should they show humans clothed or naked? A simple photo of human anatomy could easily offend future viewers who might have very different ideas of modesty, or none at all. Yet hiding the human body might send the wrong message too, suggesting that we were ashamed of our own form. In the end, they decided to include diagrams of human anatomy and reproduction, much like medical textbooks, but to avoid explicit photographs. Should they include images of war and violence? War, after all, was a real part of human history, but Sagan and his team ultimately decided against it. They wanted the golden record to offer a hopeful picture of humanity, focusing on what unified us rather than what divided us. Images of people eating, working, laughing, and learning made the final cut. Scenes of suffering and conflict did not. sound was just as important. The Golden Record included a selection of music from around the world, not just Western classical music, but also traditional songs from cultures across Asia, Africa, and the Americas. Bach was there, but so was a wedding song from Peru and an Azerbaijani folk melody. The team wanted the music to show humanity's emotional range: joy, sadness, longing, celebration. Choosing the music sparked its own debates. Some argued for including more popular music of the time, rock and jazz for example, to show the living energy of Earth's culture in the 20th century. Others worried that popular music might not age well or might seem trivial to future listeners. Time was short, and in the end, the selection leaned more toward traditional and classical pieces, with a few more recent works included, like Chuck Berry's Johnny B. Good. Even that choice was debated. Was a rock and roll song appropriate for an interstellar message? In the end, the team decided that joy and fun were as important to show as science and reason. There were also spoken greetings, short messages recorded in 55 different languages, from ancient Sumerian to modern English, Chinese, and Arabic. Each greeting was just a few seconds long, saying things like hello or peace and happiness to all. Some were formal, others were more casual. Together, they formed a chorus of voices from around the world, offering a simple but powerful welcome. One of the most emotional parts of the Golden Record was a collection of natural sounds, the Earth's soundtrack. There were recordings of thunder, birdsong, the roar of a volcano, the cry of a baby, the sound of a heartbeat. These sounds were chosen to give an alien listener a sense of what it would be like to stand on Earth, to feel its rhythms and life. Adding to the personal nature of the record was a recording of Anne Druyan's brainwaves and heartbeat. In a deeply symbolic gesture, she underwent a brain scan while thinking about the history of Earth, human civilization, and her own feelings of love. Her brain's electrical activity was captured and encoded onto the record. In a way, a piece of her consciousness now travels through space with Voyager, carrying not just facts about humanity, but a piece of human experience. The record was made of copper and then plated with gold for protection. It came with a cartridge and a needle, along with simple diagrams showing how to play it. These diagrams were carefully designed to be understandable to beings who might not share our language, mathematics, or sense of time. The entire package was sealed in a protective aluminum case, mounted on the side of the spacecraft. The team knew that whatever they placed aboard Voyager might outlive humanity itself. It might drift through space for billions of years, long after Earth was gone. It could be the only trace of us anyone would ever find. It required the team to think not just like scientists, but like artists, historians, and philosophers. They had to imagine how humanity might be seen through the eyes of strangers, beings who might be as different from us as we are from insects or trees. They had to boil down the messy, sprawling, complicated story of human life into a small, golden snapshot. Beyond the lens, Voyager's specialized instrument suite explained. The spacecraft carried a suite of instruments carefully chosen to study the outer planets and the space beyond them. Each instrument had a specific job. Together, they gave Voyager the ability to see, feel, and even hear the distant worlds it would pass. One of the most important instruments was the imaging science system. It included two cameras, a wide-angle camera and a narrow-angle camera. The wide-angle camera was used for capturing broad scenes, like the full disks of planets, groups of moons, and long sweeping shots of rings. The narrow-angle camera zoomed in to capture fine details, such as the cracks on Europa's surface or the swirling storms of Jupiter. Both cameras used Vidicon tubes, a technology similar to the early television cameras of the time. They did not capture digital images as we are used to today. Instead, they created pictures by scanning a target line by line, sending the information back as radio signals. Attached to the cameras were a series of color filters. By taking images through different filters, red, green, blue, ultraviolet, and others, scientists could build color images and also study the chemical makeup of planetary atmospheres and surfaces. The photopolarimeter system measured the brightness and polarization of light. This told scientists about the structure and composition of surfaces and atmospheres. For example, by studying the way sunlight scattered through Saturn's rings, the photopolarimeter could reveal the size and nature of the ice particles making up the rings. Next was the infrared interferometer spectrometer and radiometer. While the cameras and polarimeter worked with visible light, this instrument studied infrared radiation, essentially heat. It measured the temperatures of planets, moons, and even the gaps between them. More importantly, it broke down the infrared light into a spectrum, letting scientists identify what gases were present. It could tell researchers things like how much methane was in the skies of Triton, or how the heat varied across Jupiter's cloud bands. To listen for radio waves naturally emitted by planets and their magnetic fields, Voyager carried the Planetary Radio Astronomy Investigation. This set of antennas tuned in to low-frequency radio waves that could not be picked up from Earth because of our ionosphere. Each planet had a unique radio signature, and by studying these, Voyager's scientists could learn about the strength and structure of magnetic fields, as well as the plasma environments around the planets. A plasma spectrometer was placed that could measure the properties of the charged particles, mostly electrons and ions, that filled space around the planets and beyond. Plasma is a kind of fourth state of matter, and in the solar system, it comes mostly from the solar wind and the magnetospheres of planets. The plasma spectrometer studied the density, speed, and temperature of this plasma, helping scientists map out the invisible boundaries where a planet's magnetic field pushed back against the solar wind. While the plasma spectrometer focused on the main flow of the solar wind, the low-energy charged particle instrument looked at slightly higher energy particles, like those trapped in the radiation belts of Jupiter and Saturn. These particles could tell a lot about the violent dynamic environments near massive planets, where magnetic fields whip and churn the space around them. And for particles with even higher energies, Voyager carried the cosmic ray subsystem. This instrument studied cosmic rays, extremely energetic particles, mostly coming from outside the solar system. Cosmic rays are among the oldest travelers in the universe, and studying them gave scientists insight into processes happening far beyond our own solar system. As Voyager moved into interstellar space, the cosmic ray subsystem became one of the most important tools, still reporting on the radiation conditions in the vast reaches between the stars. The magnetometer was mounted at the end of a long boom, extended away from the spacecraft to minimize interference from Voyager's own magnetic field. The magnetometer measured the strength and direction of magnetic fields around the planets and in interplanetary space. The plasma wave subsystem listened for the vibrations of plasma. Plasma waves can produce radio signals when the particles interact with magnetic fields. By studying these signals, Voyager could detect things like bow shocks, the solar system equivalent of a sonic boom, where the solar wind slammed into a planet's magnetic field. The ultraviolet spectrometer studied light at wavelengths too short for human eyes to see. It was especially useful for studying thin atmospheres and gas clouds. Each of these instruments had to work together. None alone could paint a full picture. Voyager was a kind of flying laboratory, with each tool playing a key part in an orchestra of discovery. There were challenges too. Some instruments had to be carefully pointed at targets. Others could work while the spacecraft was spinning or tumbling. Energy use was tightly managed. Data rates dropped with distance, so not every observation could be sent home at once. Choices had to be made about what was most important, often long before the spacecraft even arrived at its targets. Because the instruments were built decades ago, they were simple compared to today's standards. They had no fancy onboard computers doing real-time analysis. Every step, when to turn on an instrument, how long to observe, what settings to use, had to be carefully planned and programmed from Earth, sometimes months in advance. The simplicity, however, turned out to be a strength. The fewer moving parts, the fewer things that could break. The instruments were rugged, and many of them continued to send back useful information, long after they were expected to fall silent. Precision in the void. Gravity assist navigation techniques. Getting Voyager to the outer planets and beyond was a masterpiece of navigation. Engineers and scientists had to find a way to reach places that were billions of miles away, with almost no margin for error. They could not just aim Voyager straight at a planet and fire it like a bullet. The spacecraft would need to use the planets themselves, their gravity, to bend its path and boost its speed. This method, called gravity assist, became one of the most important techniques behind Voyager's success. The idea of using a planet's gravity to change a spacecraft's course wasn't new. Earlier missions like Mariner 10 had tested it by swinging past Venus to reach Mercury. But for Voyager, gravity assist would be absolutely necessary. Without it, Voyager would not have had enough fuel or speed to visit multiple planets. It would have been limited to just 1 or 2 destinations at most. Gravity assist would allow Voyager to visit Jupiter, Saturn, Uranus, and Neptune in one long sweep. Planning for this was like solving a huge 3-dimensional puzzle. The engineers only had a small window in the late 1970s to launch Voyager and take advantage of the planets lining up. Missing the window would mean missing the grand tour completely. Voyager had to fly very close to each planet, skimming along just the right path so that the planet's motion would sling the spacecraft forward, like a stone whipped from a slingshot. At Jupiter, for example, Voyager would fall into the planet's massive gravity well, gaining speed as it approached. Instead of crashing into Jupiter, it would swing past, stealing a little of the planet's orbital energy and shoot out even faster than it came in. This gain in speed was dramatic. Voyager 1, after its Jupiter flyby, left the planet traveling about 35,000 miles per hour relative to the Sun. Without gravity assist, reaching speeds like that would have required a launch vehicle far bigger and more powerful than anything available at the time. The math behind these maneuvers was incredibly complex. Planners had to calculate not only the paths of the planets, but also the tiny forces acting on the spacecraft, like solar radiation pressure and gravitational pulls from moons. Even small mistakes in trajectory planning could mean missing a planet by thousands of miles. The calculations were done using the best computers of the time, but also heavily double-checked by hand and by teams working independently. One important concept used in planning was called the patched conic approximation. In simple terms, it meant treating the spacecraft as falling into the gravity well of one planet at a time, ignoring the rest of the solar system until the flyby was complete. After that, Voyager would be placed on a new orbit around the Sun, aimed at the next target. Timing was everything. Voyager's encounter with each planet had to happen at exactly the right place and the right time. Even small changes in the arrival time could make a big difference in the final trajectory. To adjust its course, Voyager carried a small propulsion system that could make tiny corrections, nudges of just a few meters per second. But these corrections had to be planned and used sparingly. After flying by Jupiter, should Voyager aim for Saturn's moon Titan, a world thought to have a thick atmosphere, or prioritize flying closer to Saturn itself? Visiting Titan would require a slightly different trajectory, one that would boost scientific return, but close off a later trip to Pluto, for instance. In the end, Titan's mystery won out. Voyager 1 was aimed to fly close to Titan, which bent its path steeply out of the plane of the solar system. Voyager 2, however, took a slightly different path, keeping it in the plane so it could continue to Uranus and Neptune. The spacecraft had to enter a precise corridor in space. If it flew too high above a planet, it would not gain enough speed. If it flew too close, it could be pulled into the atmosphere or crash into a moon. The required precision was often measured in just a few hundred kilometers, a tiny distance compared to the vastness of space. The execution of these flybys was done through carefully timed burns of the spacecraft's thrusters. Engineers would measure Voyager's position and speed using tracking stations on Earth, calculate how far off it was from the ideal path, and then plan a correction. Once the plan was sent up, Voyager would carry out the maneuver on its own, as there was no way for Earth to react in real time because of the long radio signal delays. Sometimes, small sacrifices had to be made. Choosing a slightly less perfect view of one moon could mean a much better setup for the next target. It was always a balancing act between immediate rewards and long-term goals. One example of precision came during Voyager 2's encounter with Uranus. Scientists wanted to fly Voyager close to Miranda, one of Uranus's smaller but more intriguing moons. Getting to Miranda required aiming for a very specific point in Uranus's gravitational field. Engineers worked for months to tweak Voyager's path, using small course corrections long before the spacecraft even arrived. In the end, the gamble paid off, giving humanity the first close-up images of Miranda's bizarre patchwork surface. The math behind these corrections was based on continuous measurements of Doppler shift, tiny changes in the frequency of Voyager's radio signals that revealed its speed relative to Earth. By carefully analyzing these shifts, engineers could refine their models and sharpen their estimates of the spacecraft's trajectory. The farther Voyager traveled, the weaker its radio signal became. At Jupiter, the round-trip time for a radio signal was about 90 minutes. By the time Voyager reached Neptune, it was nearly 8 hours. This meant that every maneuver and every decision had to account for a long delay, making immediate control impossible. Voyager had to operate with some level of autonomy, carrying out pre-programmed sequences that had been carefully tested and rehearsed on Earth. Gravity assist navigation also helped Voyager bend its trajectory to reach new targets. Without the gravitational kicks from Jupiter, Saturn, and Uranus, Voyager 2 could not have lined up its path to reach Neptune. The success of these maneuvers still amazes mission planners today. They often describe it as shooting an arrow at a tiny moving target from thousands of miles away, with wind and rain altering the flight path, and still hitting the bullseye. Gravity assist turned what seemed like impossible distances into a navigable pathway across the solar system. Divergent paths, plotting Voyager 1 and Voyager 2's unique trajectories. When Voyager 1 and Voyager 2 left Earth in 1977, it would have been easy to imagine them traveling side by side, twin explorers moving through space on the same path. But the truth is, even before launch, their journeys were meant to be different. The two spacecraft were launched about 2 weeks apart. Voyager 2 actually left first, on August 20th, 1977. Voyager 1 followed on September 5th. The launch windows, the periods during which each spacecraft could depart to take advantage of the planet's positions, were tight. If they missed their windows by even a few weeks, they could have lost their chance completely. Voyager 2's earlier launch reflected a more cautious approach. It was placed on a slower path, one that would reach Jupiter and Saturn later than Voyager 1. This gave engineers a chance to work out any problems with Voyager 1, which was sent on a faster trajectory. In a way, Voyager 2 was a backup. If Voyager 1 failed, Voyager 2 would still have time to adjust its mission and attempt to complete some of the same goals. But there was another important difference. Voyager 1 was aimed directly at a close encounter with Titan. At the time, Titan was thought to be one of the most promising places to study, because it seemed to have something no other known moon in the solar system had: a thick atmosphere. Scientists believed Titan might even hold clues to the early Earth. To fly by Titan, Voyager 1 had to be directed along a path that, after the encounter, would send it up and away from the plane of the solar system. This was a one-time choice. By selecting a close flyby of Titan, the mission planners knew that Voyager 1 would not be able to continue on to Uranus and Neptune. It was a sacrifice made for a specific scientific reward. Voyager 2 stayed closer to the ecliptic, the plane in which most of the planets orbit the Sun. After Saturn, if Voyager 2 remained healthy, it could continue on to Uranus and Neptune, using additional gravity assists to reach these distant worlds. This plan allowed Voyager 2 to become the first, and so far only, spacecraft to visit Uranus and Neptune. Voyager 1 reached Jupiter in March 1979, while Voyager 2 arrived in July of the same year. This spacing gave mission teams time to process Voyager 1's findings and adjust Voyager 2's plans accordingly. In fact, lessons learned during Voyager 1's flybys led to important tweaks in Voyager 2's observations, helping scientists get even better data. After its Titan flyby, Voyager 1's new trajectory pointed it steeply northward, out of the plane of the solar system. It entered a region of space far from the main planetary orbits, on a journey toward interstellar space. After their planetary encounters, both spacecraft entered into escape trajectories, paths that would carry them forever away from the Sun. Voyager 1, boosted by its close Titan flyby, achieved a higher speed relative to the Sun. It became the fastest and first spacecraft to reach interstellar space, crossing the heliopause, the boundary where the solar wind meets the interstellar medium, in 2012. Voyager 2 crossed the heliopause later, in 2018. Its path, tilted southward compared to Voyager 1's northward exit, gave scientists a second data point on the shape and nature of the heliosphere, the giant bubble formed by the solar wind around our solar system. The unique paths also influenced how Voyager's team managed communications. Because of the growing distance and the different directions, the Deep Space Network, the system of giant radio antennas around the world, had to schedule different time slots and strategies for communicating with each spacecraft. Maintaining contact with two spacecraft flying away from Earth in different directions required precise coordination, especially as their signals grew fainter and slower. Even today, long after their planetary flybys are complete, Voyager 1 and Voyager 2 are taking readings of the interstellar environment. Their divergent paths mean they are sampling different regions of space, giving scientists a more complete picture of what lies beyond the solar system. Jupiter's hidden halo, discovery of the faint main ring. When Voyager 1 sped past Jupiter in early 1979, it captured hundreds of images of the giant planet. The main focus at first was on Jupiter's massive cloud bands, its colorful storms, and its giant moons. But hidden in the flood of data was a ring around Jupiter. A ring so faint and thin that it had never been seen from Earth, even with the best telescopes. Saturn's broad, bright rings were obvious and well studied. Other planets were not thought to have them. Jupiter, with its powerful magnetic field and roiling atmosphere, did not seem like the kind of world that would host such delicate structures. But the Voyager cameras, designed to capture fine detail in very low light, were able to detect features invisible from Earth's ground-based observatories. Scientists wanted to use Voyager's cameras to search for faint objects around Jupiter, small moons, dust clouds, or anything that might be hidden near the planet. Part of this plan involved imaging the area around Jupiter while looking back toward the Sun. By aiming the cameras at just the right angle, with the Sun behind the planet, they could catch sunlight scattering off any dust particles that might be there. It was not an easy process. The glare from Jupiter itself was overwhelming, filling most of the camera's field of view. The exposure times had to be just right, long enough to catch faint light, but short enough to avoid washing out the images. The engineers and scientists had to work together to design imaging sequences that could peel back the brightness and let hidden structures emerge. When the images came back, they revealed a thin, bright line in the faint light just beyond Jupiter's edge. It was a ring, narrow, ghostly, and delicate, circling the planet. The ring was invisible in direct sunlight. It could only be seen when backlit by the Sun, in what astronomers call forward scattering. The dust particles were so tiny and sparse that they barely interacted with light unless viewed from this special angle. Further analysis showed that Jupiter's ring system was not just one ring, but had a few components. There was a main ring, narrow and relatively dense compared to the others, and then a much fainter, broader halo inside it. There was also a very tenuous, wide disk of dust extending outward, called the Gossamer Rings, which was only later fully revealed with images from Galileo and other missions. The main ring was remarkably thin, only a few hundred kilometers wide compared to Saturn's rings, which stretch out tens of thousands of kilometers. Its presence said something important about the environment around Jupiter. It meant that small impacts and ongoing processes were constantly creating and maintaining a ring of dust. The images suggested that the material in the main ring was mostly tiny dust grains. These grains likely came from small moons orbiting close to Jupiter. Micrometeorites, tiny rocks traveling through space at high speeds, smashed into these moons, blasting dust off their surfaces. Because Jupiter's gravity is so strong, the dust settled into orbit around the planet, forming a ring. This was different from how Saturn's rings were believed to have formed. Saturn's rings are mostly made of ice and are much more massive. It hinted at a different kind of process, one more common and widespread, where any large planet with moons and impacts might end up with a faint dust ring over time. Voyager's detection of the ring opened new questions. Scientists wondered how stable the ring was, how fast the dust particles fell into Jupiter, and how new material was added to replace what was lost. They also realized that other planets might have rings too. If Jupiter had a ring so faint that it could only be seen under very special conditions, then perhaps Uranus and Neptune might have them as well. In fact, when Voyager 2 reached Uranus and Neptune, it did find rings around both. These rings were also dark and faint. The idea of rings as a normal feature of giant planets, rather than a rare oddity, started with Voyager's detection of Jupiter's hidden halo. The discovery shaped future missions. When Galileo was sent to orbit Jupiter in the 1990s, one of its tasks was to study the rings in more detail. Galileo's images, taken much closer to Jupiter, showed that the main ring had sharp edges and was connected to tiny moons, including Adrastea and Metis, that orbit close to the planet. The impacts on these moons were the likely source of the ring material. In the months following the Voyager encounter, scientists pored over the images again and again. Every frame of faint scattered light was studied. They mapped the shape of the ring, measured its brightness, and compared it with models of dust behavior around a planet. They even speculated about how long the ring had existed. Some theories suggested it was constantly replenished and might have only been in its present form for a few million years, a short time compared to Jupiter's age. Voyager's discovery also reminded mission planners that the regions near large planets could contain hidden hazards. Future spacecraft would need to account for the possibility of encountering dust and small debris, not just in the broad spaces between planets, but in the very environments they hoped to explore. Radiation belt revelations, redefining Jupiter's magnetosphere. Before Voyager's arrival, scientists knew Jupiter had a magnetic field and suspected it had radiation belts, but they had no idea just how extreme the environment really was. The data Voyager sent back forced a complete revision of what scientists thought they knew about the largest planet's magnetic domain. Earth's Van Allen belts had been discovered in the late 1950s, and they were already understood to be a serious factor in planning spacecraft missions. Instruments had shown that Earth's belts could damage electronics and harm astronauts if they stayed too long within them. Based on earlier studies, scientists thought Jupiter would have similar belts, but on a somewhat larger scale. Pioneer 10 and 11 had flown by Jupiter earlier in the decade and had picked up hints that Jupiter's radiation might be stronger than expected. Still, it wasn't until Voyager 1 arrived, equipped with far more sensitive and detailed instruments, that the true scale of the danger was revealed. The charged particle instruments on board Voyager were designed to measure the number, type, and energy of the particles flooding space around Jupiter. As the spacecraft moved closer to the planet, the readings began to spike. The levels of radiation were so intense that they at times threatened to overwhelm the detectors. Voyager's particle counters registered streams of electrons moving at nearly the speed of light, densities of energetic ions that were many orders of magnitude higher than anything found near Earth, and bursts of radiation strong enough to pose a threat even to spacecraft electronics hardened against such conditions. The magnetic field of Jupiter itself was found to be enormous, stretching millions of kilometers into space. Its magnetosphere, the region dominated by its magnetic field, was bigger than the Sun as seen from Earth. Within this giant bubble, trapped particles whipped around at tremendous speeds. The belts closest to the planet were the most dangerous, packed densely with highly energetic electrons and ions. One of the major findings was that Jupiter's radiation belts were not uniform. Instead, they were layered and structured, shaped by the planet's magnetic field lines and influenced by the volcanic activity on its moon Io. Io, spewing sulfur and oxygen into space through its active volcanoes, was found to be feeding Jupiter's magnetosphere with fresh material. These atoms were quickly ionized and swept up by the magnetic field, joining the radiation belts and adding to their intensity. Even at distances many times greater than Jupiter's own radius, the spacecraft was still passing through regions thick with fast-moving particles. Inside the belts, some areas showed sudden surges in particle flux, regions where the density of radiation could jump by factors of 10 or more over very short distances. This showed that Jupiter's magnetic field was dynamic and turbulent, constantly shifting and creating areas of intense radiation pressure. The most dangerous areas were found near Io's orbit. In this region, called the Io plasma torus, Voyager measured some of the highest particle densities and energies in the solar system outside of the Sun itself. The plasma torus formed a thick, donut-shaped ring of charged particles, aligned with Io's orbit but co-rotating with Jupiter's magnetic field. This plasma environment was so energetic that it glowed in ultraviolet light, although Voyager's particle instruments were concerned more with counting and characterizing the individual particles moving through space. Engineers on Earth were closely monitoring Voyager's health during this time. Even with shielding and redundant backups, there was real worry that the intense radiation belts could do lasting harm. Careful flight planning minimized exposure by adjusting Voyager's trajectory, but it still had to pass through dangerous zones to achieve its science goals. Voyager's findings forced scientists to rethink what a planetary radiation environment could be like. The levels of particle flux measured near Jupiter were thousands of times greater than those near Earth. No previous spacecraft had ever operated successfully inside such an extreme environment. Understanding these belts became critical not only for Voyager's own mission, but for future missions like Galileo. Galileo had to be specially hardened to survive long-term operations within the radiation belts. Another surprise was the variety of particles Voyager detected. Not only were there the expected electrons and protons, but also heavy ions, sulfur, oxygen, and sodium, moving at tremendous speeds. These heavier ions were traced back to Io's volcanic plumes. Each time Io erupted, it injected new material into Jupiter's magnetosphere, feeding the belts and changing their structure. This connection between a moon's volcanic activity and a planet's radiation belts was completely new to science at the time. Voyager also discovered that the radiation belts varied over time. They were not static, but showed fluctuations, growing stronger or weaker over periods of hours or days. Some of these changes seemed linked to Jupiter's rapid rotation, which takes only about 10 hours. As the giant planet spun, its magnetic field and the trapped particles within it were churned, creating waves and shocks within the belts. Other variations were linked to solar activity. When the Sun sent bursts of charged particles into space, they could interact with Jupiter's magnetosphere, adding energy and causing changes in the structure of the belts. All of this new information built a far more complex picture of Jupiter's environment than had been imagined before Voyager. Rather than a simple, scaled-up version of Earth's radiation belts, Jupiter's system was a dynamic, violent place where charged particles moved in vast streams, controlled by an enormous and active magnetic field, fed by volcanic gases from Io, and constantly shifting in response to internal and external forces. Voyager's particle data continued to be analyzed long after the spacecraft had moved on. The information helped refine models of how radiation belts form and behave, not just at Jupiter, but around other planets as well. It informed the design of future spacecraft not only for Jupiter, but for other missions expected to encounter harsh radiation environments, such as Cassini at Saturn. Io's fiery heart, uncovering volcanic plume mysteries. Known before the mission mainly as a colorful, cratered body, Io revealed itself to be the most volcanically active place in the solar system, erupting with giant plumes of molten rock and gas that reached hundreds of kilometers into space. As Voyager 1's infrared instruments scanned the surface of Io, they picked up unexpected hotspots, areas far warmer than the surroundings. These hotspots were not evenly distributed. They were concentrated in patches, glowing brightly in thermal images. What the instruments were detecting was surface material hundreds of degrees hotter than anything expected from normal sunlight heating. The initial reaction was cautious. Could the instruments be picking up some sort of error? Or perhaps there were different surface materials that absorbed sunlight differently. The Voyager team carefully checked the data. They saw that the thermal anomalies stayed in the same places across multiple observations. They rotated with Io's surface as the Moon spun, suggesting that they were linked to fixed locations rather than fleeting atmospheric effects or sensor noise. The conclusion was becoming hard to avoid. Io had active heat sources. Something was happening under its crust. Ultraviolet imaging gave another clue. Voyager's ultraviolet spectrometer detected strange plumes of gas, faint and glowing against the blackness of space. These plumes were towering and thin, made mostly of sulfur and oxygen, both products of volcanic activity. Some of these plumes rose over 300 kilometers above the surface, forming giant, umbrella-shaped clouds that spread out and then fell back to the Moon. These ultraviolet observations were subtle. They required careful analysis to distinguish the faint light from the much stronger glow of Jupiter and the Sun. But once seen, there was no mistaking it. Io was erupting. The thermal hotspots were locations where lava was erupting from beneath the surface. The ultraviolet plumes showed where material was being thrown violently into space, escaping Io's thin atmosphere and feeding Jupiter. One of the most famous plumes, later named Pele after the Hawaiian goddess of volcanoes, was captured rising out of a giant volcanic depression near Io's equator. The thermal instruments recorded Pele's source as extremely hot, far hotter than any other location on Io. The ultraviolet sensors recorded the giant plume of sulfur dioxide gas and dust arching high above the Moon. The data matched models of volcanic eruptions on Earth, but on a much grander scale. On Earth, the most powerful eruptions might throw material tens of kilometers into the sky. On Io, the lower gravity and lack of thick atmosphere allowed eruptions to tower hundreds of kilometers high. As Voyager 1 continued its observations, it became clear that volcanic activity was not rare on Io. It was widespread. Multiple hotspots were identified across the surface. Some showed evidence of fresh lava flows. Others showed bright deposits of sulfur and sulfur dioxide that had settled from earlier plumes. Io was not a frozen, dead world, but a place of constant, violent change. Scientists back on Earth were astonished. Before Voyager, the idea that a small rocky moon could be so geologically active had seemed unlikely. Geological activity was expected only on large planets like Earth, or maybe Mars. Smaller bodies like Io were assumed to have cooled long ago. But here was direct evidence of ongoing volcanic activity, reshaping Io's surface on timescales of days, months, and years. The explanation for this unexpected heat came from another line of study, tidal heating. Jupiter's immense gravity, combined with the gravitational pulls of Europa and Ganymede, forced Io into an eccentric orbit. As Io orbited, it was constantly flexed by these gravitational forces. This constant squeezing and stretching generated internal friction, which heated the interior of the Moon. It was this heat, not leftover warmth from formation or radioactive decay, that fueled the volcanic activity seen by Voyager. Voyager 2, passing by several months later, confirmed the findings of Voyager 1. Although its path took it farther from Io, it managed to detect some of the same thermal hotspots, showing that the volcanic activity was not a one-time event, but a persistent feature of the Moon's life. Later missions would study Io's volcanic activity in more detail, but it was Voyager that first opened the door. The spacecraft revealed a hidden world of fire and gas, completely overturning old ideas about how moons should behave. The data gathered by Voyager's infrared spectrometer and ultraviolet spectrometer remain a goldmine of information. Thermal maps showed the distribution of heat across Io's surface, helping to identify new volcanic centers even when they were hidden from visible cameras by darkness or by cloud cover. Ultraviolet imaging captured the dynamics of the plumes, showing how they expanded, cooled, and eventually settled back onto the surface or escaped into space. Each observation added to the growing sense that Io was a world in its own right, with its own internal engine and its own complex history. Even today, the discovery of Io's volcanic activity stands as one of Voyager's most iconic scientific achievements. It left scientists eager to look closer at other moons, wondering what other hidden worlds might be waiting to be found. Europa's chaotic crust. signs of subsurface ocean activity. While Io was stealing the spotlight with its erupting volcanoes, another of Jupiter's moons was quietly revealing mysteries of its own. Voyager's cameras turned their attention to Europa, a bright, smooth-looking world wrapped in a shell of ice. At first glance, Europa seemed calm, almost boring compared to the fiery drama on Io. But a closer look at the images Voyager sent back showed a surface full of strange patterns, long cracks, ridges, and regions of chaotic, broken ice. Without intending to, Voyager had gathered the first real hints that something remarkable was happening beneath Europa's frozen crust. When the first high-resolution images of Europa were examined, scientists were surprised by how few craters they could find. Most of the rocky bodies in the solar system, like the Moon or Mercury, are covered with craters from billions of years of impacts. Europa, however, seemed strangely smooth in many areas. A surface with few craters suggested one thing: youth. Something had erased or buried the old impacts. That something, it turned out, was hidden movement under the ice. The network of cracks stretching across Europa's surface, some hundreds of kilometers long, didn't look random. Many were organized in patterns, curving and intersecting like veins in a leaf. Some cracks showed ridges running alongside them, twin walls rising up above the surrounding plains. These double ridges hinted that the cracks had opened and closed again, squeezing material upward in the process. At first, scientists wondered if the cracks could be caused by tectonics like on Earth, where shifting plates reshape the surface. But Europa's thin ice shell and small size made the idea of tectonic plates unlikely. Another explanation slowly took hold. The ice was being stretched and pulled by tides from Jupiter's powerful gravity. As Europa orbited, the gravitational pull from Jupiter flexed the Moon back and forth, just like it did with Io, but less violently. Over time, this flexing created stresses in the ice, forming long fractures and faults. Then there were the areas that looked completely chaotic. Instead of smooth ice or simple cracks, these regions seemed jumbled, like broken ice flows jammed together. Scientists began calling them chaos terrain. Blocks of ice the size of cities appeared to have broken apart, drifted around, and then refrozen in new positions. Some pieces were tilted or rotated, as if floating on some softer material below. This was not the kind of surface one would expect if the ice was solid all the way down. It looked more like ice floating on a liquid or slushy layer. The idea that took shape was bold for its time. Beneath Europa's icy shell, there might be an ocean of liquid water. That ocean, kept warm by tidal heating, could be shifting and cracking the ice above it. If true, it would make Europa one of the most important places in the solar system for studying the possibility of life beyond Earth. Voyager's cameras didn't have the resolution or the instruments to confirm the presence of an ocean directly. They couldn't see below the surface. But the patterns of the cracks, the low number of craters, and the chaotic terrains all pointed to a dynamic living crust shaped by something from below. Adding to the case was the color of Europa's surface. In some areas, Voyager's images showed reddish streaks running along cracks and ridges. Scientists suspected these colors came from minerals or salts, possibly carried up from the ocean below through fractures in the ice. The surface material might be contaminated with briny fluids that froze after reaching the cold vacuum of space. Though no chemical analysis was possible with Voyager's tools, the visual clues were strong enough to keep scientists debating and planning for future missions. The Moon's brightness changed in subtle ways as it rotated, suggesting a very smooth, icy covering with few mountains or deep valleys. A thick, brittle shell sitting atop a softer, shifting layer of water or warm ice would match what Voyager saw. All these pieces together told a story of a world that was not a frozen rock like Earth's moon. It was a world with energy, movement, and perhaps even a subsurface environment where life could exist. It was the start of a new way of thinking about the outer solar system. Before Voyager, moons were thought of mostly as dead, cratered relics. After Voyager, scientists began to look at them as active places with complex histories. The discovery of Europa's strange surface raised urgent questions. How thick was the ice? Was the ocean global or patchy? How much energy was being pumped into the ocean by tidal forces? And most exciting of all, could something be living down there, in the dark, warmed by hydrothermal vents or chemical energy? Voyager couldn't answer these questions. Its job was to fly by and take snapshots, not to stay and investigate deeply. But the seeds were planted. Every mission that followed, Galileo, and eventually Europa Clipper and JUICE, would be shaped by the clues Voyager found in those cracked and chaotic plains. The simple fact that chaos terrain existed at all was one of Voyager's most important finds. Breaking and moving massive slabs of ice requires energy and mobility underneath. It hinted at processes operating over tens of millions of years, reshaping the Moon's face again and again. Scientists used models of ice behavior to estimate that Europa's ice shell could be only a few kilometers thick in some places, thin enough to allow surface features to be affected by currents or convection below. Some researchers proposed that chaos terrain formed when warmer plumes from the subsurface ocean rose up, melting the ice and weakening it from below. Others suggested that pockets of water could open temporarily, allowing the surface to collapse and refreeze. Both ideas pointed to active processes that needed liquid water somewhere beneath the frozen skin. Looking back, the data Voyager collected on Europa seems almost modest compared to modern spacecraft capabilities. But in its time, those images were groundbreaking. They forced planetary scientists to rethink what kind of worlds might hide liquid water, and by extension, rethink where life might be found in the solar system. Electrostatic phenomena in Saturn's rings. When Voyager reached Saturn and began observing its rings, one strange phenomenon stood out, a phenomenon that couldn't easily be explained by the simple physics of orbiting ice and rock. These were the spokes, faint, ghostly streaks that seemed to float across Saturn's rings, shifting and changing with time. The spokes were first seen in images taken by Voyager 1 during its approach to Saturn in late 1980, as the spacecraft sent back pictures of the planet's broad, complex ring system. A few frames revealed large, radial features that stretched across the normally sharp and flat rings. These features looked a bit like the spokes of a wheel, reaching outward from the inner rings toward the outer edges. But unlike solid spokes, they were blurry, wispy, and temporary. They would appear, fade, move, and sometimes vanish completely within hours. At first, there was a debate over whether these features were even real. Perhaps they were a trick of lighting or an artifact in the images. But repeated observations by Voyager and careful analysis of the photographs confirmed they were not illusions. The spokes were truly there, and they were doing something the classical physics of orbiting particles didn't predict. Understanding the rings starts with remembering that they are made up of countless small particles, ranging from dust-sized grains to chunks the size of houses. These particles orbit Saturn at incredible speeds, but because of the laws of orbital motion, the inner particles move faster than the outer ones. If you disturb a section of the rings, the disturbance should shear and stretch quickly as particles at different speeds pull apart. But the spokes did not behave that way. Instead, they seemed to move together across wide stretches of the rings, almost as if they were connected somehow. Scientists began to suspect that something beyond gravity was at work. The leading idea that took hold was that the spokes were related to electrostatic forces, forces that come from electric charges building up on particles. In the environment around Saturn, there is plenty of energy to create static electricity. The rings are constantly bombarded by sunlight and charged particles trapped in Saturn's magnetic field. When the particles in the rings are struck by these energetic sources, they can accumulate tiny electrical charges. If enough particles in one area became similarly charged, they could start repelling or attracting each other slightly, creating changes in how the dust and small ice grains clump together or spread apart. Intriguingly, the charged particles could be lifted slightly above the surface of the rings, creating a thin dusty cloud that would scatter sunlight differently than the larger uncharged pieces below. This theory fit with what Voyager saw. The spokes were most often visible when the rings were seen at low angles to the Sun, conditions that would make thin layers of dust much easier to spot. They were also seen to rotate with the same period as Saturn's magnetic field, rather than the faster speeds expected from simple orbital motion. That clue tied the phenomenon to the planet's magnetosphere rather than pure mechanical effects. To study them more carefully, scientists examined their behavior over time. Some spokes formed very quickly, in as little as 5 minutes. Others seemed to drift across the rings, staying coherent for hours before fading away. Their birth and death seemed to be linked to changes in Saturn's magnetic environment, suggesting that sudden bursts of charged particles or variations in magnetic fields could trigger the formation of new spokes. They tended to appear most often in the B ring, Saturn's densest and brightest ring. The B ring's particles are packed closely together, providing an environment where small electrostatic effects could spread quickly among neighboring particles. The fine dust responsible for the spokes would be difficult to see in looser regions, where larger gaps separate clumps of material. There were still puzzles, though. Scientists needed to understand how relatively weak electric fields could lift material against the pull of Saturn's gravity. Dust grains are tiny, and their mass is very small, but even so, the forces required were not trivial. Some models proposed that rotating magnetic fields sweeping through the rings could induce currents in the particles, generating magnetic forces that acted in concert with electrostatic ones to levitate the dust. Voyager's instruments, including magnetometers and plasma detectors, helped add data to these models. They showed that Saturn's magnetic environment was dynamic and complex, shaped by the planet's fast rotation and interactions with its moons. Changes in this environment could easily influence the behavior of charged dust near the rings. Sometimes the spokes would be numerous, appearing all across the B ring. Other times they would be rare or absent. This variability hinted that their formation depended on temporary conditions, such as solar wind changes, magnetic storms, or variations in the density of the ring dust itself. Before Voyager, it was easy to imagine the rings as orderly bands of material, quietly orbiting forever. The discovery of the spokes, along with other structures like waves and braids, showed that the rings were lively, dynamic, and subject to a range of forces not fully understood. Although Voyager could not solve every aspect of the spoke puzzle, it opened a new field of research. Scientists realized they needed to think of the rings as an environment influenced by both gravity and electromagnetic forces operating together. Later missions, such as Cassini, would continue the investigation, providing even more detailed images and measurements. But the first clues were Voyager's gift. The spokes showed that even in one of the oldest, coldest regions of the solar system, new and surprising activity can still take place, shaped by the invisible forces of electricity and magnetism. Voyager's images captured these fleeting structures, leaving behind evidence that even today is not completely understood. Titan's haze, pre-Cassini atmospheric insights from Voyager. Titan had been a subject of scientific curiosity long before Voyager launched. From Earth-based telescopes, it was already known that Titan was wrapped in a thick atmosphere, but those early views could only tell scientists so much. The real details about Titan's atmosphere and what might lie beneath it were hidden by that same hazy covering. Voyager was equipped with new tools that could finally start to peel back that layer. In visible light, Titan appeared as a blurry orange sphere with no surface features at all. Unlike Earth's moon, which shows mountains and craters even from far away, Titan looked completely smooth. Its atmosphere was not just thick, it was completely opaque in visible wavelengths. That orange color was the first hint of what was happening in the upper layers. Voyager's ultraviolet spectrometer showed striking evidence of a complex atmosphere. The UV data showed that Titan's haze was made up of multiple layers stacked on top of each other like blankets. Each layer scattered sunlight in a slightly different way, and by carefully studying how the light was absorbed and re-emitted, scientists could start to figure out what the haze was made of. The early analysis suggested that Titan's smog was composed largely of hydrocarbons, molecules made of hydrogen and carbon. These hydrocarbons were being produced high in the atmosphere, where ultraviolet light from the sun broke apart methane molecules. When methane molecules are exposed to energetic UV radiation, they split into smaller fragments, which then recombine into heavier, more complex compounds like ethane, acetylene, and more exotic substances. Over time, these compounds condensed into tiny particles that floated down through the atmosphere, creating the thick haze that blanketed Titan from top to bottom. Long before life began here, Earth's own atmosphere may have been filled with methane and other simple gases. Titan offered a kind of time capsule, preserving those ancient conditions. In fact, many scientists began to think of Titan as a frozen laboratory, where organic chemistry, the chemistry of life's building blocks, was still happening without interference. Voyager's instruments also measured the temperature of Titan's upper atmosphere and found it to be incredibly cold, around -180 degrees Celsius. Despite the thick atmosphere, Titan was no warm haven. The haze layers trapped some heat, but the distance from the Sun and the nature of the chemicals involved meant that Titan remained an icy world. Measurements suggested that the surface pressure on Titan was greater than the pressure at Earth's surface, perhaps as much as 1.5 times higher. This was unusual because no other moon in the solar system had an atmosphere anywhere near this thick. Even planets like Mars, much larger than Titan, had thinner air by comparison. However, despite these major advances, Voyager still couldn't see Titan's surface. The haze was just too dense, and the instruments aboard the spacecraft were not designed to penetrate it fully. This limitation set the stage for future missions, but it also left scientists with many questions. Was there a liquid ocean under that haze? Were there seas of methane and ethane on the surface? Could there even be some form of primitive life? Before Voyager, Titan was a point of light through a telescope, with little real information. After Voyager, Titan was understood to be a world with a thick, chemically active atmosphere, hiding surface secrets that would take decades more to explore. The atmosphere itself turned out to have fine layers, like the stratosphere on Earth, and Voyager's ultraviolet spectrometer helped tease out some of these structures. Scientists realized that seasonal changes, driven by Titan's long, slow orbit around Saturn and Saturn's own tilt, might cause shifts in the haze layers. The UV measurements suggested that some haze layers could thicken or thin over time, depending on how much sunlight Titan received at different points in its orbit. Another detail Voyager uncovered was the presence of a detached haze layer, a kind of floating ceiling high above Titan's main cloud deck. This detached haze wasn't fully explained at the time, but it hinted at complex atmospheric circulation patterns, including winds, rising plumes, and possibly large-scale chemistry happening far above the surface. All of this laid critical groundwork for the Cassini-Huygens mission, which arrived at Saturn nearly 25 years later. Cassini carried much more sophisticated instruments, including radar that could see through the haze to the surface below. It was able to map Titan's continents, lakes, and river systems of liquid methane and ethane. It was able to watch seasonal changes unfold across Titan's atmosphere in real time. But without Voyager's early reconnaissance, Cassini would have flown blind. Voyager gave mission planners the first maps of Titan's atmospheric composition, temperature structure, and photochemistry. It provided the first data showing that Titan's smog was not just a featureless blanket, but a rich, dynamic system shaped by solar energy and internal chemistry. Those early images of Titan's orange, featureless globe became iconic. They captured the mystery and promise of Titan, a world that looked boring on the outside but was, in fact, hiding one of the most fascinating environments in the outer solar system. Voyager's encounter with Titan became one of its most significant scientific legacies. Even today, some of the questions Voyager raised about Titan remain. New missions are being planned to return, not just to orbit Titan again, but to land, to float, and even to fly through its atmosphere. Saturn's stratospheric surprises, unanticipated atmospheric waves. Voyager's instruments measured how radio signals from the spacecraft bent and changed as they passed through Saturn's atmosphere toward Earth. By analyzing these distortions, scientists could infer the temperature, pressure, and density of the different layers of Saturn's gaseous envelope. What they found was far from the uniform, banded atmosphere many had assumed. High above the thick clouds of ammonia and water, Voyager found signs of atmospheric waves rippling through Saturn's stratosphere. These waves were not like ocean waves on Earth. They were gravity waves, disturbances caused when buoyancy tries to restore balance to displaced parcels of air. Gravity waves on Earth cause things like the rippling clouds you sometimes see above mountains. On Saturn, however, they were moving through an atmosphere that was colder, deeper, and layered in ways still not fully understood. The data showed slight but regular shifts in density and temperature at certain altitudes. Instead of smooth, gradual changes, the atmosphere had wiggles, ripples that hinted at powerful forces at work. The size, spacing, and shape of these disturbances pointed directly to gravity waves. In some places, the temperature would rise slightly, then drop, then rise again over distances of just a few tens of kilometers. These gravity waves did not produce large visible features like Saturn's famous belts and zones. They were hidden signatures in the density and temperature profiles of the atmosphere. Scientists had to piece together models of how energy from below, perhaps from deep convection or storm systems, could ripple upwards, creating waves that grew stronger as they reached the thin, upper layers, where the air pressure was almost non-existent. Beneath the calm, pastel-colored clouds, the planet was pulsing with unseen energy. Warm parcels of gas were rising and falling, pushing and pulling against the surrounding atmosphere in slow but powerful patterns. The energy driving these motions might come from within Saturn itself, since the giant planet gives off more heat than it receives from the Sun. Near Saturn's equator, the waves seemed different from those near the poles. This hinted at complex circulation patterns, including something like a jet stream in the stratosphere. On Earth, jet streams are fast-moving air currents that can influence weather patterns. On Saturn, similar currents could be shaping not just weather, but also the slow migration of chemical species and haze particles high in the atmosphere. The waves seemed to show signs of vertical propagation, meaning they didn't just move sideways, but also up through the atmosphere, carrying energy from lower altitudes into the stratosphere. In the thinner air up high, these waves could grow larger, like ocean swells rising as they approach the shore. Eventually, some waves might break, depositing energy and momentum and driving further changes in Saturn's atmospheric circulation. Without such vertical mixing, it would be much harder to explain some of the temperature differences Voyager detected between different latitudes. It also raised questions about seasonal effects. Although Saturn's year is almost 30 Earth years long, the planet still experiences seasons. Voyager's data hinted that the energy and motion linked to gravity waves could shift with the seasons, although a single flyby could not provide enough information to confirm it. One challenge Voyager scientists faced was separating the true atmospheric waves from noise in the data. Measuring slight changes in temperature and density from millions of miles away is a delicate task, and it required careful calibration and analysis. The team compared measurements taken as the spacecraft moved toward and away from Saturn, cross-checking to ensure that the patterns they saw were real and not artifacts of the instruments or transmission glitches. As the analysis matured, confidence grew that Voyager had truly detected something remarkable. Not just weather, not just broad belts and zones, but small-scale dynamical processes that tied the entire atmosphere together. Gravity waves, born deep below, shaping the far reaches of Saturn's sky. These findings also prompted comparisons with other planets. Earth's atmosphere is full of gravity waves, often generated by mountains or storms. Jupiter's atmosphere, as later observations showed, also harbors such waves. Seeing them on Saturn suggested that gravity waves might be a universal feature of gas giants, a fundamental process for moving energy around planets too large and cold for sunlight alone to stir. Voyager's glimpse into Saturn's stratosphere was brief, but it was enough to open new questions. How strong were these waves? How deep did they originate? What role did they play in the formation of Saturn's polar structures, like the hexagon discovered later? The spacecraft could not answer these questions directly, but it made sure that future missions would ask them. Uranus's magnetic oddity, tilted fields, and novel auroras. When Voyager 2 approached Uranus in January 1986, mission scientists expected to find a magnetic field much like those at Jupiter and Saturn. Those two giant planets had powerful, roughly centered magnetic fields that were aligned, more or less, with their rotation axes. Their magnetospheres acted like giant protective bubbles, deflecting solar wind particles and creating spectacular auroras at the poles. Voyager 2's instruments were ready to measure another example of this kind of system. Instead, as Voyager 2 closed in on the ice giant, its magnetometer readings started behaving strangely. Rather than seeing the regular signals that would indicate a steady, planet-centered magnetic field, the data showed the magnetic field flipping and swinging wildly. It became clear that Uranus's magnetic field was not just tilted, it was tilted at an extreme angle of about 60 degrees relative to its axis of rotation. Not only that, but the center of the magnetic field was offset by nearly a third of the planet's radius from the core. In simple terms, Uranus's magnetic field was wildly lopsided and heavily tilted. The readings showed that as Uranus spun, its magnetic field swung around like a lawn sprinkler. This strange geometry created a magnetosphere that twisted and rolled as the planet rotated, causing a constantly changing interaction with the solar wind. In most planets, the magnetosphere has a relatively stable shape, compressed on the side facing the Sun and stretched out into a long tail on the night side. But Uranus's magnetosphere flopped around in unpredictable ways, reshaping itself every few hours. How did Uranus's magnetic field become so odd? The best explanation is tied to the planet's unique rotation. Uranus's spin axis lies almost flat in its orbit around the Sun. In other words, it rolls around the Sun like a ball rather than spinning like a top as Earth does. This unusual tilt likely came from a massive collision early in Uranus's history, possibly with a body several times the size of Earth. If such a collision tilted the planet without fully mixing its interior, it might have left the magnetic field generating dynamo out of alignment with the planet's spin. On Earth, the magnetic field is generated by the motion of molten iron, deep in the outer core. At Jupiter and Saturn, metallic hydrogen under high pressure creates their fields. But Uranus, being smaller and colder, probably generates its magnetic field in a thin shell of electrically conductive fluids, possibly a mixture of water, ammonia, and methane surrounding a rocky core. Voyager 2's instruments also detected auroras at Uranus, but they were very different from the bright, colorful displays seen at Jupiter and Saturn. Instead of strong, stable auroral ovals around the magnetic poles, Uranus's auroras were faint, patchy, and chaotic. They were detected in ultraviolet wavelengths by the spacecraft. The faintness and scattered nature of Uranus's auroras fit with the chaotic magnetosphere. Since the magnetic field lines were swinging wildly around, the locations where charged particles could funnel into the atmosphere and produce auroras were also shifting unpredictably. This made the auroras much harder to detect and study. Before this, it was thought that a strong magnetic field needed to be well aligned with a planet's spin, produced by a deep planet-wide dynamo. Uranus showed that there could be other configurations: shallower dynamos, localized effects, and wildly tilted fields. Voyager 2 measured the magnetic tail trailing behind Uranus, finding that it was not simply stretched out by the solar wind, but twisted into a long corkscrew shape. As the planet rotated, the rolling magnetosphere wound the magnetic tail into a spiral, carrying the odd tilt and wobble far downwind into interplanetary space. Charged particles trapped within Uranus's magnetosphere moved along the twisted magnetic field lines, creating belts of radiation around the planet. But once again, the patterns were not neat and tidy. The belts were lopsided and uneven, shaped by the distorted magnetic field and the strange way it interacted with the solar wind. The encounter with Uranus lasted only a few hours, but the data gathered during that brief window changed our understanding of planetary magnetism. Later observations from Earth-based telescopes and the Hubble Space Telescope confirmed that Uranus's auroras and magnetospheric behavior were just as unusual as Voyager had suggested. However, no spacecraft has visited Uranus since Voyager 2, so much of what was discovered during that brief flyby remains the best and only direct information. Voyager's magnetometer team faced many challenges interpreting the data from Uranus. Since the spacecraft had only one chance to fly past the planet, careful planning was critical. They had to time measurements precisely to catch the changing magnetic field at different distances and latitudes. After the encounter, it took years of detailed analysis to fully understand what the raw data meant. Early models of Uranus's magnetic field were rough, but over time, better simulations showed how a lopsided, tilted shallow dynamo could match Voyager's findings. Understanding Uranus's magnetic field helps scientists think about exoplanets that may have even stranger magnetic fields. It also shows that the conditions needed for a magnetic field are more flexible than once thought. A planet doesn't need to have a deep, massive core spinning perfectly in line with its rotation. It can be messy, tilted, and still have a field strong enough to carve out a space in the solar wind. Uranus's sideways spin, pale blue color, and cold atmosphere were already unusual. But the discovery of its off-kilter magnetosphere added a deeper, invisible layer of complexity. As with so many of Voyager's findings, the answers it delivered opened up new mysteries, ones that continue to inspire scientists decades after that cold January flyby. Triton on display, cryovolcanism unveiled at Neptune's moon. By the time Voyager 2 finally reached Neptune in August 1989, it had already traveled more than a decade through deep space. Its visit to Neptune would be its last major planetary encounter before it moved outward into interstellar space. Scientists eagerly awaited what it would find around the solar system's windiest and most distant giant. While Neptune's atmosphere and storms quickly captured attention, Neptune's moons, Triton, also delivered some surprising discoveries. Early images showed that Triton's surface was smoother than expected. Craters were few and far between, and the color images showed a pale pink and white world, suggesting a mixture of ice and exotic frozen gases. Scientists quickly realized Triton must be geologically young on the surface, with some process at work, erasing old marks. As Voyager 2 approached closer, dark streaks appeared against the bright surface of Triton. These streaks were thin, straight, and extended for kilometers. At first it wasn't clear what they were. Some thought they might be cracks or fault lines in the ice. But then, the cameras caught something even more telling: faint dark plumes rising above Triton's surface. Voyager's narrow-angle camera recorded several such plumes, reaching heights of up to 8 kilometers before bending sideways, carried by thin winds in Triton's weak atmosphere. These plumes left behind the dark streaks that were earlier noticed. Here was direct evidence of active cryovolcanism, volcanoes that didn't spit out molten rock, but instead erupted with slushy ice, liquid nitrogen, or gas. Voyager's infrared sensors helped confirm what the cameras saw. These instruments could detect temperature variations across Triton's icy surface. The plumes seemed to originate from relatively warmer spots. In absolute terms, Triton was incredibly cold, with surface temperatures around 38 Kelvin, or about minus 235 degrees Celsius. But even a slight increase in warmth was enough to make a difference when dealing with frozen nitrogen and methane. The leading explanation was that sunlight, weak though it was at Neptune's distance, was still strong enough to slightly warm darker patches on Triton's surface. These areas absorbed more sunlight than the surrounding bright ice. The warmth caused subsurface nitrogen to vaporize, building up pressure until it burst through the ice above. What erupted was a mixture of gas and fine particles, creating the towering plumes and painting dark streaks downwind. Scientists were fascinated. Cryovolcanism had been suspected on outer solar system bodies before, but Voyager's view of Triton was the first clear, direct observation of it in action. Besides the plumes, Voyager's images revealed strange landforms, smooth plains, pits, ridges, and what looked like frozen flows. Some areas resembled cantaloupe skin, a nickname scientists gave to a region of rough, closely packed hills about 30 kilometers wide. This odd terrain suggested slow, icy convection below the surface, where warmer material might rise and colder material sink, similar to movements inside Earth's mantle, but on a frozen world. Elsewhere, Voyager found what looked like lakes or frozen seas of water ice mixed with other chemicals, possibly ammonia or methane. The way the light reflected off these areas suggested different textures and compositions, a patchwork of frozen deposits shaped by active resurfacing. Triton, although orbiting Neptune now, may have been a captured object, possibly once a dwarf planet like Pluto, brought into Neptune's orbit long ago. Its odd retrograde orbit, moving in the opposite direction to Neptune's rotation, supported this idea. Voyager's instruments carefully tracked the plumes over time, noticing their behavior. Some seemed to remain active for hours. The winds, measured at just a few meters per second, bent the rising columns of material, shaping them into graceful arcs. These winds also gave scientists the first insights into Triton's thin atmosphere, composed mostly of nitrogen with traces of methane. Even though Triton's atmosphere was incredibly thin compared to Earth's, it was enough to carry fine particles away from the plume vents, spreading dark deposits across hundreds of kilometers. The sheer scale of the plume activity caught mission planners by surprise. Triton's discovery of active cryovolcanism posed new questions about energy sources in the outer solar system. Traditional models assumed that far from the Sun, bodies would be cold, dead, and unchanged for billions of years. But Triton suggested otherwise. It implied that other forces, perhaps internal heat left over from formation, radioactive decay, or even weak tidal forces from Neptune, could drive surprising levels of activity. Voyager's limited flyby meant that much about Triton remained unknown. The spacecraft had only a few hours of close-up imaging, covering roughly 40% of the Moon's surface in good detail. Still, in that short time, it made Triton one of the more intriguing bodies in the solar system. The dark streaks, the towering plumes, and the shifting icy landscape offered a rare glimpse into a kind of geological activity that was utterly alien to anything seen before in the solar system. It was a reminder that volcanic activity didn't have to mean molten lava and red-hot mountains. It could mean icy geysers spraying nitrogen gas under a feeble sun, shaping a pink and white world millions of kilometers from Earth. Neptune's dark spot, tracking transient storm systems. Neptune had been almost invisible from Earth's surface in anything but the best telescopes. Much of what scientists knew came from tiny points of light, fuzzy readings, and guesses based on the planet's similarities to Uranus. Voyager's mission was to change that. It would not only capture the first close-up images of Neptune, but would also help decode the behavior of the planet's atmosphere. Among the biggest surprises was the discovery of the Great Dark Spot. It was a massive storm system that Voyager's cameras caught almost immediately as the spacecraft began taking detailed images. It looked somewhat like Jupiter's Great Red Spot, though it was darker, deeper in color, and seemed to be composed of different atmospheric materials. In size, the Great Dark Spot was enormous, roughly as wide as Earth itself. Scientists had anticipated finding a bland, featureless atmosphere like that of Uranus, which Voyager had visited 3 years earlier. Neptune, it seemed, would be similar, since it was even farther from the Sun and should have less energy to drive weather patterns. Instead, Voyager found a dynamic atmosphere full of violent activity. The Great Dark Spot stood out immediately because of its dark, elliptical shape and the high, bright clouds that seemed to skim above it, casting thin shadows onto the atmosphere below. These bright clouds were thought to be made of methane ice crystals, floating above the main layers of Neptune's atmosphere. Their presence gave scientists a sense of the vertical structure of the storm, suggesting that the dark spot itself was a deep, possibly descending column of gas, surrounded by high-flying, fast-moving winds. Voyager's images allowed researchers to track the movement of the Great Dark Spot across Neptune's face. It moved westward, opposite to the planet's eastward rotation, much like how Earth's hurricanes sometimes drift. Measurements showed that the winds around the Great Dark Spot were among the fastest recorded in the solar system, with speeds reaching up to 2,100 kilometers per hour. These supersonic winds baffled scientists. Despite Neptune's great distance from the Sun and its cold environment, it somehow managed to produce storms stronger than any seen on the other gas giants. The dark spot was not alone. Voyager also found other features: a smaller dark spot dubbed D2, located south of the Great Dark Spot, and a bright, high-altitude cloud system near Neptune's equator that researchers nicknamed the Scooter because of its rapid movement. These features indicated that Neptune's atmosphere was far livelier than previously thought, with multiple storms, jet streams, and possibly wave systems interacting to create a complex, shifting environment. Voyager's close passes allowed for precise measurements of the Great Dark Spot's drift. Scientists calculated its latitude and speed almost hour by hour as Voyager transmitted fresh data back to Earth. Observing how the storm moved helped piece together Neptune's internal structure. Like Jupiter's Great Red Spot, Neptune's Great Dark Spot was thought to be a giant high-pressure system, a massive vortex driven by internal heat rather than sunlight. This made sense because Neptune emits more heat than it receives, just like Jupiter and Saturn. However, there were differences. Whereas Jupiter's red spot had been known for centuries and appeared stable, Voyager's scientists quickly realized that Neptune's Great Dark Spot was likely a more temporary feature. Its edges appeared rough and broken, and it was surrounded by turbulent cloud activity that hinted at a more unstable system. The storm might last for months or years, but not centuries. After Voyager's flyby, the storm's fate became a mystery for a time. Earth-based telescopes, using adaptive optics and the Hubble Space Telescope, tried to follow up on Voyager's findings. When Hubble finally turned its instruments toward Neptune in the mid-1990s, the Great Dark Spot was gone. In its place, Hubble found other dark spots, new ones appearing in different locations. This confirmed that Neptune's dark spots were transient, forming and fading over relatively short timescales. It suggested that the planet's atmosphere was not only highly dynamic, but also capable of reorganizing itself completely in a matter of years. Scientists theorized that the Great Dark Spot might have dissipated when atmospheric waves disrupted its stability, or that it simply migrated deeper into the atmosphere, becoming invisible to optical instruments. Unlike the thick, colorful clouds of Jupiter, Neptune's atmospheric layers were thinner and less chemically varied, making it easier for features to vanish from sight without truly disappearing. By observing the drift of the Great Dark Spot and the behavior of nearby cloud systems like the Scooter, scientists pieced together a better understanding of Neptune's atmospheric circulation. They found that the planet's upper atmosphere was organized into bands moving in opposite directions, similar to but less clearly defined than those on Jupiter and Saturn. The Great Dark Spot sat between two of these bands, in a region where shearing forces could help sustain a vortex temporarily. Voyager's instruments measured that Neptune emitted roughly 2.6 times the energy it received from sunlight. This internal energy, likely left over from the planet's formation and slow gravitational contraction, helped drive the fast winds and energetic storms. Voyager's brief visit captured the Great Dark Spot at its peak, a snapshot in time of one of the solar system's most powerful and ephemeral weather systems. The swirling clouds, fast winds, and shifting features of Neptune revealed that even in the cold and dark reaches of the outer solar system, planets can be filled with incredible energy. Crossing the termination shock, Voyager 1's boundary breakthrough. After decades of steady travel, far beyond the last planets of the solar system, Voyager 1 approached a boundary that had only been theorized when it first launched. Scientists called it the Termination shock, a zone where the solar wind slows down sharply as it begins to collide with the thin gases and magnetic fields of interstellar space. Unlike the moments when Voyager 1 passed planets, this was not a visible event. There were no photographs to capture, no dramatic landscapes. The evidence came from instruments quietly measuring the invisible environment around the spacecraft. As Voyager 1 pressed further outward, its sensors picked up subtle changes. One of the first clues was a noticeable drop in the speed of the solar wind around the spacecraft. Instruments built to detect the flow of charged particles and the direction of magnetic fields started reporting data that looked different from what had been seen closer to the Sun. The solar wind had been racing outward at supersonic speeds, but now it seemed to slow and become turbulent. The crossing itself wasn't like flipping a light switch. Scientists back on Earth spent months examining the data, trying to pinpoint exactly when Voyager 1 had crossed the termination shock. Because the spacecraft was so far away, over 90 astronomical units from the Sun, the signals took more than 12 hours just to reach Earth. Every bit of information had to be carefully analyzed, compared with models, and tested against expectations. The instruments that played a key role during this period included the plasma science experiment, the cosmic ray subsystem, and the magnetometer. The plasma science instrument was designed to directly measure the properties of the solar wind. But by the time Voyager 1 reached the outer heliosphere, that instrument had already stopped functioning due to earlier system failures. This made the job harder. Scientists had to rely more heavily on indirect clues. The cosmic ray subsystem, still working, recorded a noticeable change in the intensity and energy of cosmic rays. These high-energy particles come from beyond the solar system, but inside the heliosphere they are partially shielded by the solar wind. As Voyager 1 moved beyond the shock, the shielding weakened and more cosmic rays reached the spacecraft's detectors. This sudden uptick was a telltale sign that the boundary had been crossed, or at least approached. The magnetometer told its own story. The magnetic field strength in the region around Voyager 1 showed a marked jump. The orientation of the field also changed. Scientists had predicted that, as the spacecraft crossed into the region where the solar wind was compressed and slowed, the magnetic field lines carried outward from the Sun would bunch up and twist. That is exactly what Voyager 1's data showed. Despite these hints, it was not immediately clear when to mark the exact crossing point. The solar system's outer regions are not cleanly divided like zones on a map. The termination shock is a moving, wavy frontier that can expand and contract based on the strength of the solar wind and the pressure of the interstellar medium. It breathes like a living thing, pulsing outward during periods of strong solar activity and pulling inward when the Sun quiets down. Voyager 1 might have crossed back and forth across the shock more than once before finally leaving it behind. After extensive analysis, scientists eventually concluded that Voyager 1 had crossed the termination shock in late 2004, somewhere around December. For the first time, humanity had sent a machine beyond the Sun's direct, strong influence into a realm where the solar wind was slowed, heated, and mixed with material from other stars. Until Voyager 1's data arrived, the nature of the termination shock had been mostly theoretical. Some models predicted it would be sharp and dramatic. Others suggested it would be broad and turbulent. Voyager 1 revealed that reality was complex. The crossing was messy, noisy, and filled with surprises. This changed how scientists understood not just the heliosphere, but also the way other stars interacted with their surroundings. Designed in the early 1970s, the spacecraft was now operating in an environment no one had fully planned for. The cosmic ray subsystem, the magnetometer, and other instruments kept working faithfully, transmitting precious data back across billions of kilometers. The spacecraft's tiny radio transmitter, using less power than a refrigerator light bulb, continued to whisper its discoveries to Earth. As Voyager 1 moved beyond the termination shock, it entered the Heliosheath, where the solar wind slows to subsonic speeds and mixes with the interstellar medium. It is a turbulent region, filled with eddies and flows. Here, Voyager 1 continued to measure particle densities, magnetic field strengths, and cosmic ray intensities, building a detailed picture of this previously hidden frontier. The data from the termination shock crossing had implications far beyond Voyager 1's immediate journey. It fed into new models of space weather, affecting predictions about cosmic radiation hazards for future astronauts. It shaped ideas about the protective bubbles around other stars, influencing studies of how life might be shielded or exposed on planets orbiting distant suns. Voyager 1's crossing of the termination shock renewed public interest in the mission. News stories celebrated the achievement. Scientists gave talks explaining what it meant to cross into the edge of the solar system. People who had watched Voyager launch in the 1970s marveled that it was still out there, still exploring, still sending back messages from farther away than anyone had ever traveled. In scientific papers and conferences, researchers continued to debate the finer details. Some argued about the exact timing of the crossing. Others discussed whether Voyager 1 had truly crossed into interstellar space, or was still within the Sun's domain. These debates were not signs of confusion, but of healthy, dynamic science. They showed that even a spacecraft operating decades beyond its original mission could still challenge assumptions and inspire new ideas. Heliosheath histories, plasma turbulence beyond the shock. The heliosheath is formed because even after the solar wind slows down at the termination shock, it does not immediately stop. It continues outward, but much more sluggishly, piling up like traffic near a bottleneck. This slow, compressed flow mixes with incoming galactic material. Voyager 1 sensors were built to detect cosmic rays and magnetic fields, so even without functioning cameras, the spacecraft could still see what was happening. One of the earliest surprises was how turbulent the plasma was. Scientists had predicted that the Heliosheath might be a calmer region after the drama of the termination shock. Instead, Voyager found a rough sea. The plasma currents showed sudden changes in direction and speed. The magnetic field bent and twisted in unpredictable ways. Rather than a smooth transition to interstellar space, the spacecraft was navigating through something closer to an invisible storm. The data revealed pockets where the solar wind was still relatively strong, mixed with other areas where the influence of interstellar particles grew more powerful. The magnetic field was expected to align more cleanly in this region, but instead, Voyager measured constant fluctuations. One moment the magnetic lines would stretch in one direction, the next they would twist in another. Cosmic rays, particularly the very energetic ones coming from deep space, are partially blocked by the solar wind inside the termination shock. In the heliosheath, Voyager measured a gradual increase in these particles. But it wasn't a smooth, gentle rise. Instead, the levels fluctuated wildly over short periods. There would be sudden bursts of cosmic rays, then dips, suggesting that Voyager was moving through turbulent zones of differing densities and pressures. Scientists started noticing patterns. Certain kinds of fluctuations seemed to repeat after weeks or months. This suggested that large-scale waves or structures were moving through the heliosheath, carried by the weakened solar wind. Some researchers compared these structures to magnetic islands, bubbles of magnetic fields moving through the swirling plasma. These islands could trap or release cosmic rays, depending on their configuration, explaining the sudden spikes and drops Voyager observed. The magnetic field was much stronger than expected. The solar wind slowdown at the termination shock caused the Sun's magnetic field lines to pile up, intensifying the field. But rather than forming a simple, steady wall, the magnetic field appeared as a tangle with folds and ripples. Even moving at about 17 kilometers per second, it took years to travel through the region. Scientists had to be patient, watching as the spacecraft sampled one tiny part of the heliosheath at a time. Each new reading filled a piece of the puzzle, but also raised questions. How wide was the heliosheath? Would it stay the same thickness everywhere, or did it balloon out in places? Were there layers inside it, like an onion, or was it all one roiling mix? The longer Voyager stayed in the heliosheath, the more it challenged earlier models. Some theories had suggested that the solar wind would become stagnant in this region. Instead, Voyager found that even here, the solar wind continued to push outward, carrying disturbances from the Sun's activity cycle, coronal mass ejections from the Sun. Massive bursts of solar plasma and magnetic fields could be detected years later as they passed through the heliosheath, creating additional turbulence. Occasionally, Voyager passed through what scientists called pressure fronts. places where the plasma density and magnetic field strength suddenly changed. These were like weather fronts in Earth's atmosphere, marking boundaries between different conditions. By the late 2000s and early 2010s, Voyager 1 was approaching the outer edge of the Heliosheath. Scientists watched closely for signs that it was nearing the heliopause, the final boundary where the solar wind's influence ends and true interstellar space begins. But the lessons learned in the Heliosheath stayed with them. They knew now that boundaries in space were not clean or sudden. They were thick, turbulent zones that could stretch for billions of kilometers. North versus South heliosphere asymmetry revealed by dual Voyagers. When Voyager 1 crossed the termination shock in December 2004, it was far north of the solar equator. Voyager 2, following a different trajectory farther south, did not cross the same boundary until August 2007, almost 3 years later. Scientists had assumed that the heliosphere would be roughly spherical, or maybe just slightly compressed on the side facing into the interstellar medium. After all, most models had pictured the solar wind blowing outward in all directions evenly, balanced against the pressure of the galactic environment. But the staggered crossings of Voyager 1 and 2 suggested something very different. Voyager 1 crossed the termination shock at a distance of about 94 astronomical units from the Sun. That means it was about 94 times farther from the Sun than Earth is. Voyager 2, on the other hand, crossed the shock at about 84 astronomical units, significantly closer to the Sun. If the heliosphere had been a perfect sphere, the crossings should have happened at about the same distance. The fact that Voyager 2 crossed the shock so much earlier and closer meant that the southern hemisphere of the heliosphere was compressed compared to the northern hemisphere. Scientists needed to rethink how the solar system's protective bubble was shaped. It wasn't just solar wind pressure versus the galactic environment. Other forces were at play, and the biggest clue pointed to the magnetic field that exists in the space between the stars, the interstellar magnetic field. Unlike the Sun's own magnetic field, which is carried outward by the solar wind, the interstellar magnetic field comes from the galaxy itself. It turns out this field presses against the heliosphere unevenly, squeezing it more on one side than the other. This discovery meant that the solar system was not drifting quietly through the galaxy inside a smooth bubble. Instead, it was being buffeted and shaped by the larger environment of the Milky Way. The two Voyagers not only crossed at different distances, but experienced different conditions while crossing. Voyager 1's passage through the shock showed a sharper transition, a more abrupt slowing of the solar wind. Voyager 2, by contrast, detected a more gradual slowing down. The solar wind's speed decreased in stages rather than all at once. This suggested that the structure of the termination shock was not like a solid wall, but more like a wrinkled, uneven frontier that varied with latitude and perhaps with solar cycle conditions. Voyager 2's plasma instruments were still working at the time of its shock crossing, while Voyager 1's had failed years earlier. This gave scientists much better data about the nature of the plasma environment during Voyager 2's crossing. They saw not just a change in speed, but also shifts in temperature and density. These measurements confirmed that the southern termination shock was not just closer, but structurally more complicated. During periods of high solar activity, the solar wind is stronger and the boundaries expand outward. During quieter periods, the solar wind weakens and they shrink. The fact that Voyager 2 crossed the termination shock during a period of declining solar activity may partly explain why it encountered the shock closer to the Sun than Voyager 1 had. Still, the differences were too large to be explained by solar activity alone. The persistent asymmetry, even after accounting for solar cycles, pointed strongly to an external pressure, the interstellar magnetic field bending the heliosphere into an unexpected shape. Some researchers even suggested that the heliosphere might be more like a comet, with a blunt nose facing into the galactic wind and a long tail streaming out behind. The Voyagers were helping to sketch out the true shape of the solar system's frontier for the first time. The discovery of the heliosphere's asymmetry also sparked debates about the long-term exposure of the solar system to cosmic rays. If the southern hemisphere was compressed, it might allow more cosmic rays to leak into that region, affecting the solar system differently depending on latitude. This raised new questions about how Earth's position relative to the heliosphere might have shifted over millions of years, and whether this could have influenced climate or even biological evolution. One of the most dramatic confirmations of the heliosphere's asymmetry came in 2012, when Voyager 1 crossed the heliopause. When Voyager 2 later crossed the heliopause in 2018, it did so at a different distance, again underscoring that the solar system's protective bubble is misshapen and dynamic. Cosmic Ray Chronicles: Unexpected Deep Space Flux Variations. Both spacecraft carried cosmic ray subsystem instruments that could track the energy and direction of incoming particles. As long as they were within the heliosphere, the Voyagers recorded how the solar wind acted like a giant shield, pushing back against the inflow of galactic cosmic rays. Inside the bubble of the solar wind, cosmic ray levels were lower than outside. But the data they returned did not show a simple, steady rise in cosmic ray intensity as the spacecraft moved farther from the Sun. Instead, the readings were full of surprising spikes and sudden drops, small storms of cosmic particles that came and went. Then, as they neared the edge of the heliosphere, instead of a simple gradual rise in particle counts, there were sharp spikes, sudden dips, and unexpected plateaus. Sometimes cosmic ray levels would rise by 20% or more over just a few days, then settle back down. Other times, they would remain steady for months before another quick change. One explanation scientists began to explore involved the structure of the magnetic fields in the Heliosheath. The Sun's magnetic field gets carried outward by the solar wind, forming a vast spiral pattern called the Parker spiral. As the solar wind slows beyond the termination shock, the magnetic field lines bunch up, fold, and tangle. This creates regions where cosmic rays can become trapped or accelerated. Magnetic turbulence can create pockets where particles bunch up, or regions where they are scattered away. When the Sun emitted coronal mass ejections, these disturbances traveled outward, eventually reaching the Voyagers even years after being launched from the Sun. These solar storms compressed magnetic fields in the Heliosheath, temporarily strengthening the solar system's shielding against cosmic rays. When one of these solar storms arrived, the Voyagers often recorded sudden dips in cosmic ray intensity, even though they were already well beyond the planets. In 2012, when Voyager 1 crossed the heliopause and entered interstellar space, the cosmic ray story reached a new and fascinating chapter. Cosmic ray detectors showed a sudden and dramatic rise in galactic cosmic rays. For years, cosmic rays had been partially blocked by the heliosphere's magnetic field. Now, beyond the Sun's influence, Voyager 1 was exposed to the full force of the galaxy's particle population. But even here, the cosmic ray levels were not uniform. There were still fluctuations, periods when particle counts would climb or fall, suggesting that even interstellar space was not perfectly uniform. Magnetic fields, turbulence, and other unseen forces were still shaping the flow of particles, even outside the solar system. One of the unexpected findings was the presence of sharp boundaries in cosmic ray intensity near the heliopause. Voyager 1 encountered regions where the cosmic ray flux changed rapidly over just a few hours or days, almost as if there were invisible walls or fences in space. These sudden changes were a strong clue that the heliopause itself was a much more complex structure than initially pictured. Voyager 2's later crossing of the heliopause in 2018 confirmed and expanded on these findings. Although it crossed the heliopause at a slightly different distance, it also recorded sudden changes in cosmic ray levels. Comparing Voyager 1's and Voyager 2's data, scientists could see that the shape and structure of the heliopause varied depending on location, and that cosmic ray propagation was sensitive to these local conditions. The Voyager's measurements challenged earlier models of how galactic cosmic rays travel through the galaxy. It had been thought that cosmic rays diffuse slowly and fairly evenly through the magnetic fields of the Milky Way. but Voyager data showed that small-scale magnetic turbulence could have a big effect on cosmic ray movement, creating traps or channels where particles could be concentrated or depleted. Interstellar magnetic murmurs, probing fields beyond the heliosphere. After Voyager 1 crossed the heliopause in 2012, it entered a place humanity had never studied directly before: true interstellar space. In this new environment, the familiar protection of the solar wind was gone. The spacecraft was now moving through the undisturbed material between the stars, a region made up of thin plasma, cosmic rays, dust, and, critically, magnetic fields that came from sources far beyond our solar system. To understand this new place, scientists leaned heavily on Voyager 1's magnetometer, an instrument designed decades earlier to measure magnetic fields at planetary distances. Now it was performing a task its designers had only dreamed about: sensing the magnetic field of the galaxy itself. Inside the heliosphere, the Sun's magnetic field dominates, twisted into a large spiral by the rotation of the Sun itself. Beyond the bubble, the magnetic field should be shaped by galactic forces, pointing in a different direction and perhaps having a different strength. However, when Voyager 1 crossed into interstellar space, the magnetic field did change slightly, but not as much as scientists had predicted. The direction shifted by only about 20 degrees, not the 90 degrees many had anticipated. It suggested that the local interstellar magnetic field was closely aligned with the field inside the heliosphere at the location where Voyager 1 exited. One possibility was that the heliosphere itself had distorted the local field, bending it around the bubble like a rock bending a stream of water. Another idea was that the field in this part of interstellar space was naturally close to the solar field's orientation. Either way, the data challenged simple models of a clean, sharp transition between solar and galactic magnetic environments. Even more interesting, Voyager 1's magnetometer recorded small fluctuations and ripples in the interstellar magnetic field. These murmurs revealed that interstellar space is not a calm, silent vacuum. It is a place where magnetic fields wiggle, twist, and vibrate, carrying information about distant events and local turbulence. Some of these ripples were thought to be relics of long-past supernova explosions, their shock waves still stirring the magnetic sea after millions of years. The strength of the interstellar magnetic field turned out to be about 5 microgauss, very close to the strength of the magnetic field carried outward by the solar wind at the edges of the heliosphere. This similarity suggested that the heliosphere's boundary was not a rigid shell pushing hard against a much stronger or weaker external field. Instead, it was more like a flexible membrane adjusting to pressures that were not vastly different from its own. Voyager 1's magnetometer also detected occasional pressure waves passing through the interstellar medium. These were linked to solar events, such as strong solar flares that had traveled to the outermost reaches of the heliosphere and beyond. When these pressure waves slammed into the heliopause, they caused a ripple effect that Voyager's instruments could pick up even in the interstellar medium. The magnetometer showed brief periods where the magnetic field strength would jump and then settle back down, much like a ship detecting the passing of a distant storm. When Voyager 2 crossed the heliopause in 2018, its magnetometer also recorded a modest change in magnetic field direction, again smaller than expected. This second crossing confirmed that the strange alignment seen by Voyager 1 was not just a one-time anomaly. The data from both spacecraft together suggested that the local galactic magnetic field, at least near our solar system, has a fairly consistent orientation. By comparing readings from Voyager 1 and Voyager 2, scientists could begin to sketch a rough three-dimensional picture of the local interstellar magnetic field. They found that the field lines were slightly draped around the heliosphere, as if the solar system were moving through a magnetic mist, bending the field gently rather than slicing through it sharply. This draping effect had important consequences for understanding how cosmic rays enter the heliosphere and how the solar wind interacts with interstellar material. The murmurs detected by the magnetometers hinted at the presence of low-frequency plasma waves in interstellar space. Although Voyager 1's plasma instruments were not operating normally, scientists could infer the density of the interstellar plasma by analyzing the way magnetic field vibrations traveled through the medium. In 2013, scientists used this method to estimate the local plasma density, finding it higher than inside the heliosphere. This provided strong confirmation that Voyager 1 had indeed left the Sun's domain and entered a region governed by galactic conditions. These plasma waves, driven by slight changes in the magnetic field, told scientists that interstellar space may be thin and cold. But it is not static. Instead, it pulses and sings in very low tones, far below the range of human hearing. The magnetometers had effectively given the Voyagers a way to listen to the galaxy's background hum. Today, with Voyager 1 over 160 astronomical units from the Sun, its magnetometer remains one of humanity's only direct links to the true interstellar environment. The instrument keeps delivering priceless information about the invisible structure of the galaxy around us. Every day it continues to operate. It adds one more brushstroke to a picture of deep space that is still being drawn, one magnetic whisper at a time. Challenges in deep space communication. Even though the Voyager spacecraft are some of the most successful missions in history, their achievements would have meant little without a way to send their discoveries back to Earth. Communicating with spacecraft billions of kilometers away was one of the most difficult technical challenges NASA engineers faced. It was not just a matter of building a strong enough transmitter or a big enough dish. It was about keeping the tiny signals aligned, hearing them through overwhelming noise, and adapting to changing conditions as the Voyagers ventured farther from home. Voyager's communication system was based on a high-gain antenna, a large, white parabolic dish about 3.7 meters across. This dish had to be pointed very precisely at Earth. Even the slightest misalignment could cause the narrow beam to miss the planet entirely. Early in the missions, maintaining the antenna's pointing was relatively easy. The spacecraft's onboard gyroscopes and star trackers allowed it to keep a steady lock on Earth, adjusting its attitude with small thruster firings when necessary. But as Voyager moved farther out, even small wobbles and drifts became serious problems. One major difficulty was the long time delay. Engineers had to predict future spacecraft behavior, not just correct past mistakes. This required highly detailed models of how the spacecraft would move and how external forces like sunlight pressure might slowly nudge it off course. Teams at JPL worked tirelessly to refine these models, constantly improving their ability to keep the antenna pointed at Earth. Another big challenge was signal strength. Radio signals fade according to the inverse square law, meaning that if a spacecraft is twice as far away, its signal is 4 times weaker. By the time Voyager reached the outer planets, the signals were so faint that picking them out of the background noise was like trying to hear a whisper in the middle of a roaring windstorm. The spacecraft transmitted with only about 20 watts of power and over billions of kilometers. That tiny signal became unimaginably faint. The solution on Earth's side was the Deep Space Network, or DSN. At the time of Voyager's launch, the DSN included facilities near Goldstone in California, Madrid in Spain, and Canberra in Australia. These sites were spaced around the planet, so that as Earth rotated, at least one station could always stay in contact with deep space probes. Even with these large dishes, some as big as 70 meters across, receiving Voyager's signals required pushing the limits of technology. Engineers developed more sensitive receivers, cryogenically cooled to reduce thermal noise. They also improved signal processing techniques, using computers to dig the faint Voyager transmissions out of the background static. Sometimes, multiple DSN stations were linked together to combine their signals, a technique known as arraying. This allowed them to detect signals that would otherwise have been too weak for any single dish to hear. As the Voyagers moved beyond Saturn and into truly deep space, these efforts were not enough on their own. The DSN itself had to be upgraded. In the 1980s, NASA launched a major program to expand and modernize the network. The 64-meter antennas were upgraded to 70 meters, giving them more collecting area. New digital systems replaced older analog ones, allowing for better error correction and data compression. These improvements meant that even as Voyager's signal weakened, Earth's ability to hear it grew stronger. But communication was not just about receiving data, it was also about sending commands. Every time a new scientific sequence was planned or a spacecraft needed a correction, teams on Earth had to encode the commands carefully and beam them up with enough precision that Voyager could hear and understand them. The spacecraft's memory was extremely limited, so command sequences had to be tightly packed and tested rigorously before being sent. A single error could cause Voyager to miss a critical observation or even endanger the mission. Another issue was bandwidth. The farther Voyager traveled, the slower its data rates became. At Jupiter, Voyager could send back images at a reasonable pace, allowing scientists to see new pictures every day. By the time the spacecraft were beyond Neptune, data rates had dropped so low that a single image could take hours to transmit. Scientists had to prioritize what data they most wanted to receive, often choosing between different instrument readings or accepting lower resolution images to save transmission time. To cope with this, Voyager's systems included a digital tape recorder, allowing the spacecraft to store data during periods when Earth's receiving conditions were poor, such as when the spacecraft was on the far side of the Sun, and then transmit the stored data later. Managing this storage was a delicate balancing act. The tape could only hold so much, and if it filled up before transmission, new data would be lost. Solar storms could create bursts of radio noise that drowned out Voyager's weak signals. Even Earth's own atmosphere could pose problems, especially from moisture and storms that affected radio transparency. DSN teams had to monitor these conditions carefully and adjust their listening schedules as needed. Over the decades, Voyager's transmitter slowly degraded. Engineers on Earth had to compensate by adjusting receiver sensitivity, slowing down data rates, and developing clever software workarounds to keep communication open. Likewise, the DSN's hardware needed regular maintenance and upgrades to continue functioning at the high standards demanded by the mission. A less obvious challenge was the human factor. Over the decades, as technology advanced and new missions launched, resources and attention naturally shifted. Maintaining a dedicated team to support Voyager's aging systems required constant effort. Knowledge had to be passed from one generation of engineers to the next, ensuring that critical expertise was not lost. This continuity became its own kind of engineering achievement, as vital as any hardware upgrade. The cumulative effect of all these efforts was that even as Voyager 1 and Voyager 2 crossed into interstellar space, they remained in touch with Earth, whispering back their data across unimaginable distances. Their success in doing so stands as a testament not only to the spacecraft's design, but to the persistent, evolving ingenuity of the DSN and the teams that supported it. Voyager's communication story did not involve dramatic pictures or headline-making discoveries. Instead, it was about the steady, determined work of keeping a fragile thread of connection alive across the darkness, adapting to new challenges year after year, and pushing the boundaries of what was possible. Without it, all the discoveries the Voyagers made would have been lost to the void, known only to the spacecraft themselves. Storage and compression strategies over 50 years. When Voyager 1 and Voyager 2 launched in 1977, the concept of digital storage was still in its infancy. Home computers were just starting to appear, and memory capacity measured in kilobytes was considered advanced. Yet NASA had to design a system that would not only store and manage data for a deep space mission, but continue to do so reliably for decades. That was robust, flexible, and able to adapt as the spacecraft moved farther from Earth and bandwidth became more restricted. It also meant thinking carefully about how data would be compressed and prioritized, a task that would evolve long after the spacecraft had left the solar system. At the heart of Voyager's storage system was a digital tape recorder. While it sounds simple, just a kind of space-age cassette, it was a core part of Voyager's ability to carry out science at all. Data collected by the spacecraft's instruments had to go somewhere before it could be sent to Earth. The tape recorder allowed Voyager to store several megabytes of data, an enormous amount by 1970s standards, and then play that data back slowly, over hours or even days, using the spacecraft's narrowband transmitter. This system ensured that no observation would be wasted. The tape was made from mylar and coated with iron oxide, designed to withstand the radiation, temperature swings, and vacuum of deep space. It could be rewound and reused, though NASA kept careful track of wear to avoid overusing one portion of the tape. The mechanism had to work in zero gravity, far from repair. Engineers included redundancy and fault detection to ensure that, if something went wrong, the spacecraft could skip over bad sections and keep operating. Data would be recorded in structured blocks. Each block had a timestamp, a source identifier, to indicate which instrument had recorded it, and checksums to help detect and correct errors during playback. That meant, even if the signal arriving at Earth was partially damaged by static or weak reception, scientists could often reconstruct the original data thanks to these internal checks. Voyager's data wasn't stored in raw form. From the start, the mission used early compression strategies to pack more science into every second of transmission time. This wasn't modern image compression like JPEGs or zip files, but simpler, purpose-built techniques. One common approach was to average or decimate the data, reducing its resolution without losing its scientific meaning. For instance, images from the spacecraft's cameras could be downsampled from their original resolution before storage, with detail sacrificed only where scientists decided it wasn't needed. Each instrument had its own rules for what could be compressed and how. Some data was also prioritized. If the spacecraft passed near a planet and captured dozens of images, mission planners might decide which ones were most important and instruct Voyager to send those first. Others might be saved for later, or even overwritten if the tape was needed for new observations. The decision-making process was careful and sometimes difficult, especially when the science team had to choose between continuing to collect fresh data and preserving earlier material that hadn't yet been transmitted. Over the years, the compression strategies evolved, not on the spacecraft, those systems were fixed, but on Earth. As computer processing advanced, the DSN could handle weaker, slower signals more effectively. This allowed engineers to slow down the data rate, but make up for it with more efficient processing on the ground. New software tools could detect patterns in the data stream and remove redundancy, effectively compressing the signal even after it had left the spacecraft. This became especially important as the Voyagers entered interstellar space. There, bandwidth was at its lowest, and many of the original high-rate science modes had to be shut down. The tape recorder was no longer used frequently. Instead, data was streamed directly from the instruments at ultra-slow rates. But that data was still valuable, and careful management ensured that it continued to flow reliably back to Earth. One clever example of Earthside data handling involved the cosmic ray detectors. These sensors picked up particle hits over time, counting and categorizing them. Instead of recording every individual event, Voyager could summarize activity in intervals, giving totals, averages, and spike events. This reduced the data load without losing key scientific insights. Later, when solar storms caused sudden changes in particle counts, engineers could examine the compressed summaries and extract meaningful patterns. Similarly, the magnetometers had their own unique format. Because they sampled the local magnetic field in 3 axes, the data was stored as small numerical values over time. These values could be smoothed or averaged over longer periods, depending on how much detail was needed. During periods of interest, like passing through a shock wave, higher resolution sampling was enabled. Otherwise, lower resolution saved space. As the mission progressed into the 1990s and 2000s, the original computers and engineers began retiring, but the need to decode and interpret Voyager's stored data continued. NASA began porting old decoding software to modern systems, a process that required careful reverse engineering of decades-old code written in Fortran or assembly language. In some cases, only printed documentation remained, and engineers had to recreate data pipelines from scratch. These efforts were crucial to preserving the ability to read and understand stored data, even as the physical tapes on the spacecraft continued spinning and recording new science. The process of storing and transmitting data from Voyager was also shaped by available power. As the RTGs aged, power budgets shrank. That forced new decisions: which instruments to prioritize, which heaters to turn off, and how long the spacecraft could stay in a given science mode. Data management had to consider power as well as memory. Recording something on the tape meant powering the instrument, the recording mechanism, and sometimes heaters to keep everything at operating temperature. Every watt was budgeted. Teams met regularly to make sure data goals could still be met under changing conditions. Eventually, the use of the tape recorder was phased out almost entirely. Today, Voyager mostly transmits data live, as a slow trickle, one bit at a time, carefully spaced and error-checked. But the legacy of those early storage and compression strategies remains. They allowed Voyager to capture full planetary flybys, record transient events like plumes and storms, and hold on to precious science until Earth was ready to receive it. Without that capacity, entire chapters of Voyager's mission would have been lost. And in an indirect way, Voyager's data management systems influenced later missions. Engineers who worked on Voyager took what they learned to missions like Galileo, Cassini, and New Horizons. Storage limits, tape wear, error correction, compression schemes all became standard engineering challenges for future spacecraft. Voyager proved that even with limited memory and old technology, careful planning could extend a mission far beyond its original expectations. Every byte that comes from Voyager today represents a victory over distance, time, and decay. The spacecraft are old, their systems worn, and their instruments running on borrowed power. But thanks to the choices made in the 1970s and the clever data strategies refined over 5 decades, they still speak, sending home fragments of the universe. On board, Gambits, how engineers rescued Voyager from system glitches. No spacecraft, no matter how carefully built, can avoid problems when stretched across decades and billions of miles. As Voyager 1 and Voyager 2 traveled farther beyond any spacecraft before, they ran into trouble. Systems glitched, instruments failed, computers locked up, and each time, the engineering teams on Earth had to figure out how to rescue a system they could no longer touch. In the early years, many of the fixes were about timing. The spacecraft were designed for planetary flybys, where a missed command or lost response could mean missing the chance to record once-in-a-lifetime data. During the Jupiter and Saturn encounters, the engineering team stayed on constant alert. If an imaging sequence stopped or a tape recorder misbehaved, they had only hours, sometimes minutes, to analyze telemetry, draft a fix, send commands, and confirm the issue was solved. One early problem came when a command timing error caused a data sequence to overlap itself, nearly corrupting the entire Saturn encounter timeline. Engineers discovered the issue and rebuilt the sequence with less than a day to spare. Later, problems got more complex. As the spacecraft moved away from the giant planets, attention shifted to long-term survival. Onboard software began showing its age, but Voyager carried something rare for its time: a flight computer that could accept software patches, even across deep space. That single capability kept the mission alive through many of its toughest moments. One of the most critical saves came in the 1990s, when Voyager 2's attitude control system began sending incorrect data to the onboard computer. The glitch caused the spacecraft to believe it was misaligned, triggering a reset of its guidance thrusters. The constant correction cycle risked wasting precious fuel. Engineers on Earth traced the issue to a memory corruption bug, likely triggered by radiation or wear in a specific memory cell. They responded by writing a new software routine that bypassed the affected memory address, isolating the problem without disabling the entire subsystem. The patch was tested on Earth simulators, uploaded to the spacecraft, and activated without issue. Another rescue involved Voyager 1's imaging system. Long after its camera was turned off, engineers noticed that the spacecraft's attitude readings were occasionally jumping by small amounts, enough to interfere with communication pointing. The culprit turned out to be a degraded gyroscope sensor. The team wrote a workaround that blended data from the sun sensor and star tracker to estimate rotation more accurately. The hybrid method wasn't as precise as the original hardware, but it was enough to keep the spacecraft on track. The communications subsystem faced its own set of problems. In 2000, engineers discovered that Voyager 1's high-gain antenna was slowly drifting off target, causing its signal to weaken. After some investigation, they found that a piece of code responsible for checking the antenna's alignment had stopped functioning properly due to an arithmetic overflow. They wrote a new algorithm that spread out calculations over several cycles to avoid the overflow, then uploaded it during a carefully timed transmission window. It worked, signal strength stabilized, and the drift was halted. Memory management was a recurring source of trouble. The spacecraft used very limited RAM, shared by multiple instruments and processes. Over time, memory leaks and fragmentation began to appear. On several occasions, instrument commands failed because the buffer had filled up with leftover data. One particularly tense moment came when the plasma wave instrument on Voyager 2 stopped responding. The data log showed no new readings, but also no clear error. Eventually, engineers suspected that a buffer overflow had locked up the instrument's internal scheduler. They issued a hard reset, followed by a special command that forced the instrument to clear its queue and resume normal operation. Patching the flight software wasn't easy. It required perfect understanding of how the spacecraft processed instructions, what memory addresses were safe to use, how long command sequences could be, and what side effects might be triggered. Engineers used Earth-based duplicates of Voyager's flight computers to test everything. These simulators were old, fragile machines kept running in NASA labs long after their original designers had retired. They ran vintage code and required vintage tools, but they were essential for practicing the uploads before sending anything to the real spacecraft. As energy levels dropped, Voyager teams realized they would eventually have to shut off heaters, which risked causing instruments to freeze. But when they tried to power off non-critical systems, a small power spike was sometimes recorded, triggering a fault response. To avoid this, they modified the power sequencing code so that switches were spaced out by milliseconds, allowing the power system to remain stable, even during shutdowns. The change was tested on both spacecraft and became standard practice. Some workarounds were more mechanical than software-based. The tape recorder mechanisms had moving parts that occasionally failed to engage. Engineers discovered that a simple change in the command sequence, adding a 1-second pause before play commands, gave the motors enough time to stabilize. That pause, added as a safety measure, prevented jams and head misalignments for years afterward. Then there was the time Voyager 2 stopped talking altogether. In 2020, after an antenna calibration maneuver, the spacecraft failed to respond. For days, NASA couldn't reach it. Eventually, they suspected that a mistimed command had left the spacecraft pointing away from Earth. Using predictions of its orbit and slow signal scanning across different angles, the team re-established contact. It was the most serious communications outage since launch, and it ended without loss of data or damage, thanks to years of discipline and diagnostics. Many of the engineers solving the issues weren't even born when Voyager launched. They relied on detailed documents, some handwritten, stored in binders and scanned PDFs. Some of the fixes required adjusting bits in memory banks directly, using low-level codes to flip a switch or rewrite a table. These weren't user-friendly systems. A single mistyped byte could disable an instrument permanently. But the teams learned to move carefully, think clearly, and test endlessly. One of the key decisions that enabled so many saves was the modular structure of the flight software. Engineers in the 1970s had grouped instructions by function: attitude control, science sequencing, telemetry formatting. That meant later teams could isolate a faulty routine and replace only that portion without touching the rest. This modularity gave Voyager a form of digital resilience that proved critical. Even now, with both Voyagers in interstellar space, engineering teams are still making fixes. They reconfigure science schedules to preserve power. They change antenna angles to maintain communication. They turn off heaters selectively to stretch the energy budget. And they continue to patch the code, sending sequences written in a language that only a few machines on Earth and 2 machines far beyond Pluto still understand. Pathfinder to the Kuiper Belt, Voyager's influence on subsequent missions. When Voyager 1 and Voyager 2 were launched in 1977, there was no plan for a Kuiper Belt mission. In fact, the Kuiper Belt hadn't even been officially discovered yet. What scientists suspected at the time was that something might exist beyond Neptune, a kind of distant leftover from the solar system's formation. But there was no solid map of that region, no targets, and certainly no specialized spacecraft headed in that direction. Yet in a way, Voyager opened that door. It did so not just by surviving long enough to reach the outer boundary of the planets, but by forcing engineers, mission planners, and scientists to rethink how far we could go and how we might operate once we got there. As Voyager pushed past Neptune in the late 1980s and early 1990s, the space community watched closely. The missions had already redefined what was possible in terms of navigation, communication, and power management at great distances. But their endurance also showed that deep space wasn't empty. There was activity out there. By the time New Horizons mission was being planned in the 1990s, Voyager's data provided critical support for its scientific case. Many of the systems that flew on New Horizons were directly influenced by what worked and what didn't on Voyager. The spacecraft layout, for example, reflected lessons in thermal balance. Voyager taught engineers that temperature swings out there were sharper and more disruptive than anticipated. New Horizons included more sophisticated thermal blankets and a better understanding of how instruments needed to be grouped to keep things both cold and stable. The onboard power system was also a direct descendant of the Voyager approach, using a single RTG. The difference was efficiency. Years of data from Voyager helped engineers predict decay rates with more accuracy, allowing them to size the generator more tightly to the expected lifetime of the mission. The science instruments on New Horizons also benefited from what Voyager lacked. Voyager's imaging systems were cutting edge for their time, but by the time they passed Neptune, their capabilities were outdated. New Horizons designers wanted a smaller, more versatile camera that could handle both wide and narrow fields, with better resolution and lighter mass. Voyager's long encounters with data bottlenecks and memory constraints made this a top priority. New Horizons featured a much faster data handling system with compression algorithms that had evolved out of Voyager's early struggles with onboard tape storage and limited downlink rates. Navigation across the outer solar system, something Voyager handled with clever timing and ground-based tracking, was upgraded for New Horizons. But the basic idea that precise trajectory adjustments could create gravity assists powerful enough to fling a spacecraft across multiple planets was Voyager's legacy. The path New Horizons took was shorter, focused on a Pluto flyby instead of the Grand Tour. But its single Jupiter gravity assist in 2007 was modeled in part on techniques Voyager engineers developed decades earlier. The importance of timing, spacecraft orientation, and instrument readiness during such maneuvers had already been mapped out, thanks to Voyager's experience during its Saturn and Uranus encounters. Voyager's long-haul conversations with Earth via the DSN showed just how fragile and slow deep space transmissions could be. New Horizons' antenna system, though smaller than Voyager's 3.7-meter dish, was more efficient and took advantage of better signal processing on the ground. The DSN itself had been upgraded in response to Voyager. New Horizons, decades later, used these upgrades during its farthest data relays, especially after the Pluto flyby, when the spacecraft had to send back huge amounts of information over many months. Voyager's ability to manage system glitches through software patches and backup routines had set a high bar. In response, New Horizons was designed with its own version of layered autonomy. It could detect faults, reroute power, reset subsystems, and enter safe mode without waiting for Earth. Voyager revealed just how dynamic the outer planets and their moons were. That understanding shaped the New Horizons science plan. Instruments were selected not just to capture Pluto's surface, but to scan its atmosphere, its temperature profile, and its interactions with the solar wind. Scientists had learned from Voyager that some of the most surprising results came not from pictures, but from invisible data. The spectral lines, the plasma readings, the subtle changes in magnetic fields. As a result, New Horizons included instruments like SWAP, or the solar wind around Pluto, and PEPSI, or Pluto Energetic Particle Spectrometer Science Investigation, to give a fuller picture, even as it zipped past in just a few hours. By the time New Horizons launched in 2006, Voyager had been operating for almost 30 years. That kind of timeline changed how mission teams thought. New Horizons was designed not just for one flyby, but for an extended mission. And once its Pluto pass was completed, it headed toward the Kuiper Belt object 2014 MU69, later named Arakoth. This continuation wasn't an afterthought. It had been part of the plan, drawn from Voyager's example of a mission that could keep going, collecting meaningful science well beyond its initial target, just like Voyager had done after Neptune. Even missions that never went to the outer solar system borrowed from Voyager's blueprint. Cassini, which orbited Saturn for over 13 years, used many Voyager discoveries to shape its own science goals. The understanding of Titan's atmosphere, Saturn's rings, and magnetosphere came first from Voyager. Similarly, the Parker Solar Probe, headed the opposite direction into the Sun's corona, used lessons from Voyager about radiation shielding and communication timing under extreme conditions. Voyager demonstrated that spacecraft could be flexible, not just physically, but mentally, in the sense of evolving code, adaptable routines, and contingency plans built years in advance. It taught engineers how to prepare for the unexpected, and taught scientists that the most interesting results often weren't the ones they predicted. Today, New Horizons continues to operate just like its predecessors. And just like Voyager, it's still sending back data from a region of space few had ever seen. Its design is different, its instruments more advanced, and its goals more focused. But the path it took was made possible by the long arc of Voyager. Not just in the hardware, but in the mindset. Keep going, keep learning, and keep the signal alive. Will we reach the Oort cloud, modeling Voyager's distant trajectory? When Voyager 1 and Voyager 2 were launched, the idea of the Oort cloud itself was still mostly a theory, something proposed by astronomer Jan Oort in the 1950s to explain why long-period comets kept appearing in the inner solar system. These icy visitors would arrive from every direction, suggesting they came from a massive spherical shell of debris far beyond the planets. But it was just a hypothesis. There was no direct evidence, and there was certainly no mission designed to go out and explore it. Yet, as Voyager continued its journey beyond Neptune, through the heliosphere and into interstellar space, the possibility began to feel less far-fetched. And people started asking, if they could last this long, could they reach the Oort cloud? Could a mission meant to visit Jupiter and Saturn become the first human object to enter one of the most distant structures around our Sun? The short answer is, maybe. But the long answer is more complicated. It has to do with the sheer distance involved, the current trajectory of the Voyagers, and what it even means to reach the Oort cloud in the first place. The Oort cloud is not like the asteroid belt or the Kuiper belt. It's not a flat ring or a band. It's thought to be a vast, spherical swarm of icy bodies that surrounds the entire solar system like a bubble. Estimates of where it begins vary. Most models suggest the inner edge could start around 2,000 astronomical units, AU, from the Sun. 1 AU is the distance between Earth and the Sun. Voyager 1, the farthest spacecraft we've sent, is currently around 160 AU from Earth. That means it's not even 10% of the way to the inner edge of the Oort cloud. To model when Voyager 1 might reach this region, scientists turn to simulations. They use precise measurements of the probe's current speed, direction, and acceleration, or lack of it, and project forward. Voyager 1 is traveling at about 17 kilometers per second relative to the Sun. At that speed, it would take over 300 years to reach the start of the Oort cloud. To get to the middle of the cloud, around 10,000 AU, would take more than 30,000 years, and to pass beyond it could take over 100,000 years. Voyager 2 is on a similar path, though slower, at about 15 kilometers per second. It's also heading in a different direction, angled slightly south of the plane of the solar system, while Voyager 1 heads north. Voyager 2 is a few years behind in terms of trajectory, and its arrival at the cloud's inner edge would take even longer. What's fascinating is how much of this is still theoretical, even in 2025. The Oort cloud has never been seen directly. No telescope has resolved its objects. Every estimate of its size and shape is based on the orbits of comets that fall toward the Sun. These orbits hint at a vast reservoir of icy debris, but the distribution, density, and even the total mass of the cloud are still debated. Some models suggest that the outer Oort cloud could extend halfway to the nearest star, up to 100,000 AU or more. That's almost 2 light-years away. This uncertainty makes trajectory modeling difficult. Scientists have to make assumptions. They take known physics, gravity, momentum, solar wind influence, and apply them to the sparse data we have. They also factor in gravitational nudges from other stars. Over thousands of years, even distant stars can slightly alter a probe's path. The Voyager spacecraft, unpowered and drifting, are especially susceptible to these influences. That said, no known stellar encounters in the next million years are expected to dramatically change their course. Voyager 1's direction points roughly toward the constellation Ophiuchus. Voyager 2 is headed toward the direction of Sagittarius. These trajectories mean both are leaving the relatively flat plane where most planets orbit and entering the wider volume where the Oort cloud is thought to spread. But even with accurate modeling, predicting when they'll actually encounter Oort cloud material is still a guessing game. The density of Oort cloud objects is believed to be incredibly low, so low that the chance of a Voyager spacecraft flying close to one is extremely slim. In fact, many simulations suggest that even after reaching the inner boundary of the Oort cloud, the Voyagers might not record any evidence of it. Even assuming their instruments were still somehow working hundreds or thousands of years in the future, they certainly weren't built to detect faint icy bodies at great distances. There are no high-resolution cameras still operating. There's no radar or infrared system capable of spotting tiny, cold objects in pitch-black space. The most likely signal would be a slight increase in dust particle impacts or subtle shifts in cosmic ray readings, but even that might not happen. The cloud is so diffuse that decades or centuries could pass without a single measurable event. Every year, the RTG's output will drop and eventually all science instruments will go dark. After that, only a faint signal, possibly just a carrier tone, will remain. Eventually, even that will stop. The spacecraft will continue to drift silently, still moving at high speed, but uncontactable. Their clocks will keep running, but Earth will no longer hear them. That silence doesn't end the journey. The probes will continue to move, orbiting the center of the galaxy like stars do. The simulations continue even after contact is lost. Scientists plot their paths for hundreds of thousands of years into the future, noting where and when they might enter denser regions of the galaxy or pass near other stars. In roughly 40,000 years, Voyager 1 is expected to come within 1.6 light-years of a star called Geyser 445. Voyager 2 will have a similar stellar encounter with Ross, 248, in about 42,000 years. One interesting twist is that even if the Voyagers never detect the Oort cloud, their flight paths might help us understand its structure. If astronomers ever find a way to detect Oort cloud objects more directly, perhaps with future telescopes or space-based infrared systems, they could trace the Voyager's location against any mapped features. The probes would become reference points in a region of space we currently know only through theory. Their movement through the cloud, even silently, would add context to what we see. In that sense, Voyager has always been about more than immediate results. It's a mission built on long timescales. Its greatest discoveries didn't always happen where or when they were expected. And on that inspiring note, today's journey comes to an end. If you enjoyed this voyage, leave a comment, leave a like, and consider subscribing to the channel. Thanks for watching,